Good morning, everyone. So today we will be having our revision session. So we'll wait for a few more minutes for all to join.
Good morning, ma'am.
Good morning, Ray.
I have a doubt in graded assignment of week 6, question 9, ma'am.
Okay. Piyusu, would you take
I have a doubt in graded assignment of week 6, question 9, ma'am.
Okay. Piyusu, would you
I have a doubt in graded assignment.
Yeah, which question? Hello, I'm audible, right? Ria is there?
Yeah, you are audible.
Yeah, Ria has asked the question, right? Okay. Yes, Ria, which question?
Week 6, graded assignment, question number 9.
Okay. Question number 9. Yeah, is my screen is visible? This question number 9. Hello?
Yes, sir, it's visible.
Yeah, okay. This question, right?
Yes, sir. So can you walk me through the steps on how to do decomposition?
Yeah. So anyway, we are going to discuss this BCNF decomposition in this session only. But for this question, I will just give you the hint. Like first, what we have to do, like for any decomposition, first we have to find out the candidate key, right? Yeah. So after finding out the candidate key, we will know which are the prime attribute and which are the non-prime attribute, right? So
Yes,
here
sir.
in this question, options are you can go through the options also, but I will suggest you that you should decompose this department till BCNF. Okay. So how to decompose that? Okay. So we have given that domains of all the attribute consist of atomic values, right? Here you can see. So we can say that from by this, like all the domains are atomic value only. So this relation department is in 1NF. Okay. So even if it is not mentioned in the question, so by default you assume that our relation is in 1NF. Okay. So it will consist of atomic values only. Now let us check for second NF. Okay. So what is the condition for second NF? Hello. Yeah.
Partial dependency.
Yeah. So for first NF, there should be no multi-valued attribute. Okay.
Yeah.
And for 2NF, there should be no partial dependency. So what I mean by partial dependency, say suppose say A determine B is there and A is a subset of candidate key, where A is a subset of candidate key. Okay. Say for example, there are A, B, C, D, 4 attributes are there in the relation, and BC is the candidate key. Okay. And if C is determining the non-prime attribute, that is T, since C is the subset of candidate key, right? So this is the partial dependency. So I can say that my relation is not in 2NF if there is partial dependencies present. Okay. So now first you have to find out the candidate key here. Then we have to find out the prime attribute and non-prime attribute and check whether this any functional dependency having the partial dependency or not. If it is having any partial dependency, so what we do, we take the closure of that particular attribute, like left hand side of the functional dependency, we take the closure of it and we simply calculate the closure and make it as a relation R1. Okay, so I guess we can solve this question. Okay, so this is for 2NF. Okay, there should be no partial dependency. Now, what is the condition for 3NF? There should be no transitive dependency, right? So what is transitive dependency? Non-prime attribute is determining non-prime attribute, right? If this functional dependency is present in a parent functional dependency, then this is a transitive dependency, and in 3NF it is not allowed, right? So we have to remove this transitive dependency. How to remove that? Just simply take the closure of those left-hand side of functional dependency and make them as a one relation. Okay. And now what is the BCNF condition? Like left-hand side of every functional dependency must be a super key, right? That means if we take the closure of left-hand side of any functional dependency, we should get all the attributes present in that relation, right? So we have to decompose this relation in BCNF. So what is the candidate key here? Anyone? What is the candidate key here? Okay, let us solve this question first. Okay, shall I solve it now, or in week 6 we can do that?
So can you please solve it now?
Okay, how many students? 115 participants. Okay, yeah. So let us find out the candidate key first. Okay, so how to find the candidate key? So first, a simple trick is that we have to find out those attributes which is not present on the right hand side of any functional dependency. Okay, so MG manager number is present. Yes. Okay, so it is confusing. So what I will do, I will consider this as A, and this is B, this is C, this is D, this is E, this is F, and this is G, right? So department number means A determine CD, not CD, CB, right? Manager number, manager name. See, I am just simply renaming this attribute, okay, ABCD, so that I can simplify this relation. So MGR number, that is C. So C determine D, right? Here department number and building number. So E and B, right? No, department number.
A and D.
A and E. Yeah, A and E will give me F, right? Employee count. Yeah. So employee count space requirement, that is F determine G. That is F determine G, and then space requirement building number. So G determine building E, right? So G determine E. So these are my functional dependency and these are my attribute A, B, C, D, E, F, G. Okay. So just for simplification, I have just considered this as a ABCD. So let us find out the candidate key first. Okay. So like the first simply trick is that just find out the attribute which is not present on the right hand side of any functional dependency, right? So CB is present, D is also present, E, F, G is present. Only A is not present, right? So A must be a part of candidate key, right? It must be a part of candidate key, not a candidate key. So let us take the closure of A first. What is the closure of A? Here from A, I will get CB, right? From A, I will get CB. Now from C, I will get D, right? From C, I will get D. Now, is there any possibility? No, right?
No, sir.
So, yeah, A is not a candidate key. Now we have to take the combination of A with all the attributes, right? Okay? So in order to find out the candidate key. But like what we have to do, we have to take the closure of AB, AC, AD, AE.
So I was given key AF and AE as candidate keys.
Okay, AE and AF, right? So here you can see ACBD is not consists in the A closure. So I can simply say that ABCD. So this cannot be my part of candidate key. Like if you practice, then you will know that okay, ABCD is already in the closure of A. So if I take the combination of ABCD with any other, still I will not get the all the attributes, right? If I take the closure of this also. So what I will do, AE. So if I take the closure of AE, what I will get from A, I will get CB, right? And from C, I will get D. So E will also be there like transitive, right? So E also present. Like from AE, so here from AE, I will get F. So I can add F also. From F, I will get G, right? So this is my relation R. I am getting all the attributes present in the relation R. Now let us find out the closure of AF. Okay. So what I will get? AF. From A, I will get CB. From C, I will get D. From F, I will get G, and from G, I will get E, right? So this is also my relation R. So AF is also a candidate key. Let us check for AG. AG. So AG, C, B. From C, I will get D. From G, I will get E. From AE, I will get F. AG is also candidate key, right?
So
Yeah. So AE, AF, AG is a candidate key. Now we have to check for other combination also, like BC, CD. So these are my candidate key or not. You can see BC, BD, CA will not be a candidate key. So what is remaining? Okay, so these three are my candidate key. Now let us check for a combination of B. BC will not be there, BD will not be there, BE. Whether B is a candidate key here?
No, sir.
No. B, if we take the combination of B with any other attribute, still will not get, right? Sorry, A is not a part of candidate key. Okay. So only we have to take the combination with A. Okay. So these three are the candidate key. Yeah. So, okay. So till now, everyone got, right? How to find out the candidate key?
yes, sir.
Yeah. So I will simply erase this. So I will write candidate keys are AE, AF, and AG. Right. So my prime attributes are A, E, F, G. Right. And remaining are the non-prime attribute. Right. So now let us check for the partial dependencies present in any of the functional dependency. Yes. Anyone? Here you can see if left hand side consists of subset of candidate. Yeah. Okay, let us check for the first one. A determines CB. Right. So A is a part of candidate key, subset of candidate key, right? Hello. And CB is a non-prime
Yes, sir.
attribute. So this is a partial dependency. C determine D. No, both are non-prime attribute, right? So first we are checking for partial dependency only. So this is basically a transitive dependency. Now AE determine F. No, this is a candidate key, right? This is not a partial dependency. So F determine G. So both are the prime attribute. This is also not a partial dependency. G determine E. These are also the prime attribute. So only partial dependency is A determines CB. Okay. So now in order to make this department in 2NF, I have to decompose that and I have to take the closure of this particular left hand side of functional dependency. So what I will get? If I take the closure of A, I will get A, C, B, and from C, I will get D, right? So I will make this as relation R1, right? Now, in order to have lossless decomposition, what are the conditions for lossless decomposition? Because our decomposition must be lossless, right? So like R equals to R1 union R2 and and R1 intersection R2 should give me R1 or R2, right? So here my R1 is ABCD. So what should be my R2? Like for this condition, I can say like all the attribute which is not present in the relation R1. Right? ACBD is there. So what I can add? ABCD, EFG, right? So EFG I can add. But now I have to add one attribute such that I will get this condition right. Like so I should get R1 intersection R2. You should determine R1 or R2. So which attribute should I add from ACBD here? Anyone or A, right? Because the intersection of R1 and R2 is A. And if I take the closure of A, I will get R1, right? So my this condition will also satisfy. Okay. So this is my 2NF decomposition. R1, R2. Now, what are the applicable functional dependencies to particular this R1? FD1. I will write it FD1. So from A, CB is there, right? And C determined is also there. AEF is not present. FG is not. Okay. For FD2, what are the applicable functional dependencies for relation R2 from the parent functional dependency? AE determine F, right? F determine G and G determine E, right? Hello? Are you getting it what I'm doing here?
So one.
Yes.
So we should also check for transitive.
Yes, yes. So as of now, this R1 and R2 in 2NF, right? In 2NF, we are only considering, we will not consider partial dependency, right? So R1, R2 are in 2NF. Now we'll check
Transitive dependencies I'm asking. Let's say A determines C, C determines B, then A determines.
This is transitive dependency, yeah.
Yeah. So we should check that as well, right?
Yeah, we should check that as well. But I'm just decomposing this department into first 2NF, 3NF, and then BCNF, right? So as of now, my relation R1 and R2 in 2NF. Okay. So if you check here, A, CB, so you can see all the functional dependency will satisfy my 2NF condition, right? Because there is no partial dependency here. Now let us check for 3NF. So in R, yes.
Let's say in the functional dependencies given for the original question, we have A determines G, then G determines C, let's say. So, yeah. And A determines G.
A determines G, okay.
By Armstrong's axiom, we can say A determines C, right?
Yes, right, yeah.
Yeah, so A determines C should also be a part of R1 in that case. Although A determines C wasn't given in the original dependency. So that's what I was asking.
That should be also part of candidate. Sorry, this particular relation.
Yeah.
Yeah. But we'll consider only parent functional dependency, right? Here, like for decomposing. Like when we check.
It's fine. But say in this question only we had something like A determines G and G determines C. Then if we only take the parent functional dependencies, then A determines C won't be a part of R1, although it should be, right?
Yeah, although it should be, but we are checking for this particular parent functional dependency. So that thing we have to do while finding out while checking dependency preservation. Okay. So in dependency preservation, what we do, we calculate the F1 closure. It is all the possible functional dependency which can be derived from the parent functional dependency. Right? Yeah.
So we'll only stick to parent functional dependencies for decomposition part.
Yeah. So if we follow just these four things, we should stick to parent functional dependency only.
Okay.
Yeah. Because when you decompose it, ultimately those partial dependency will get eliminated if you decompose that. So what you was saying, like A determine G, right? And G determine
C. So A determines C.
Yeah. So here you can see, right? A determines CB. So already A determines C and A determine B is there.
No. For
okay,
this,
if it is not present, right?
I made up an example.
Okay. Yeah.
So should we stick to parent dependencies or should we do?
But sorry, but usually if decomposition into 2NF and 3NF is dependency preserving, right? Always. Only when it gets into BCNF, we can lose dependency.
But it should be lossless decomposition, then only it will be dependency preserving, right?
Yes, that's correct. So the point about losing a dependency will not arise if we do it to 2NF and 3NF, as long as we do it lossless.
Yeah. So till BCNF, okay, in BCNF we can get lossless decomposition with dependency preserving and or not preserved. Yeah. Okay.
Sir, and just one other question. In case there is any partial dependency where on the left hand side one key is a prime attribute and one is a prime attribute and another is a non-prime attribute. Yes. What will we do in that case? Will we treat it as a partial dependency? Like for example, here A, E both are prime attributes. A, E determines F. What if we had something like AG or not AG, or let's say AC or something, AC determining B?
If it is determining non-prime attribute, then we can consider it as a partial dependency.
Okay, even though one of it is a prime attribute.
Yeah.
Okay.
For these cases, you can watch one session we have taken the week 6, like Professor Nirav Bhatt has taken that session. You can watch that.
Sure.
Okay, so what we are doing here?
Should I take only the parent functional dependencies, or should I apply the axioms rules and check as well?
No, we should check for the parent functional dependency only. Okay, so when we are considering this, like we are following this step, right? First we'll see for 1NF, then 2NF, then 3NF, and then BCNF. So then in that case, we can consider for a parent functional dependency. But what you are talking about, if you directly want to convert this from this relation R into 3NF or BCNF, so for that we need to consider canonical cover of this functional dependency, right? In the slide you must have seen, first we find out the canonical cover, and then we make each of the functional dependency as a one relation.
Yes.
Yeah. So in that case, in finding out the canonical cover, you will remove those particular redundant functional dependencies. So that's what you're talking about. So it will cover all the functional dependency, right? Okay. But here I am just taking, like I am just decomposing this into 2NF, 3NF, and then BCNF. Okay. We can consider one example like this only. Okay. I have one example. I will take that. Okay. Don't. Okay. Okay. So this my R1 and R2 are in 2NF now. Now what is 3NF decomposition? Okay. So what is the condition? There should be no transitive dependency. So in R1, which one is the key here for R1? Yes, anyone? A is the key, right? Yeah. So A is the key here, right? So my prime, so non-prime attribute are B, C, and D, right? So here you can see my left-hand side is a super key here, right? So it will satisfy my 3NF condition. But this thing you can see, C determined, it is a non-prime attribute determining another non-prime attribute, right? So this is my transitive dependencies. I have to remove this particular transitive dependency. So what I will do, I will decompose this relation R1 into R3 and R4. Okay. So what I will do, I will take the closure of CD here. So the closure of CD, what I will get? CD only, right? Hello?
Yes, sir.
Yeah. So what should be my R4 in order to have a lossless decomposition? AB must be there. Should I add C or D here in the R4?
C.
The intersection should get the should be a key of any of the attribute, right? So if I add C here, so R1, so the R3 intersection R4 will give me R3. Okay. So this is my R3, this is my R4. Now if you see, C determined is applicable here and A determined CB is applicable here. In both the relation, left hand side is a super key, right? For this relation R3, C is a super key. For this relation R4, A is a super key, right? Hello, are you getting it? What I'm saying?
Yes, sir.
Yeah. So this R3 and R4 in BCNF, right? Because left hand side is a super key, right? Yeah. Now let us check for R2. So what is the key for R2 here? What is the key? Just 1 minute. Yeah. So what is the key here? AE, right? AE from F. I will
E
get
or AG?
AE and AG. Yeah, right. So AE and AG are my key here. So my prime attribute are AE and G. So here you can see AE determine F. So this is a key, right? So F determine G. So here G determine is also a prime attribute, right?
So AF
is also a candidate key, right? Right. AF is also a candidate key. So AE, B, F. So any transitive dependencies present in this relation?
No.
Hello?
Sir.
No. So my this relation R2 in 3NF also, right? But not in BCNF. This relation R2 is in 3NF. So let us check for BCNF. Here A, E determine F, right? So this is satisfying my BCNF condition.
and
This
G
is
are
not satisfying, right?
Yeah.
So what I will do, I will take the closure of F, I will get FG. I will take the closure of G, I will get GE, right? Now here you can see I can directly write it as F determine E also, right?
Closure of F would be FGE, right?
Sorry. Yeah, yes, I'm right. FGE. FGE, right? Yeah. But if you see here, like what are the applicable functional dependency here? F determine G and G determine E here, right?
Yes, sir.
So this will not satisfy my BCNF condition here. And what you were talking about earlier here, you can see F determine G is present and G determine E is present, right? So I can say F determine E also here, right?
Yes, sir.
Yeah. So what I will do, I can consider F closure also, but simply I will do, I will decompose this relation R2 in AEF, FG, and GE. So then all the three relation will be in BCNF.
So I didn't understand this part. Since F determines G and G determines E don't satisfy BCNF condition, we will decompose it. So one relation would be F closure and G closure.
So this is my AEF and FGE. So I'm decomposing this R2 in R5 and R6. Okay. But here, what are the applicable functional dependencies? F determine G and G determine E, right? So this will not satisfy my BCNF condition. And again, I will decompose this into FG and GE, right? So I will get AEF, FG, and GE.
So why are we not calculating G closure?
We calculate the G closure only. Now from that only we are getting GE, right?
My understanding is that since we have two functional dependencies that don't satisfy the BCNF condition, we would have R5 as F closure, R6 as G closure, and R7 as remaining attributes plus the common attribute, like we were doing previously.
That's what we are doing now. We are taking closure of AE and F closure and G closure here.
So G closure would be GE. So one relation should have FGE, other relation should have GE, and other one should have the remaining.
No. So if you take these two relation, yeah. So you are talking about this FG and FGE, right? So basically these two attributes are present in this relation only, na? Why will I make the separate table for this two attribute?
No, I didn't get this part. Shouldn't we make one relation containing the attributes belonging to F closure? So that would be FGE, and another relation with attributes of G closure, which is GE, because F determines E and G determines E both don't satisfy the BCNF properties.
Okay, so
So,
Yes.
but the actual step would be to first do, I mean, I think you've maybe done it in one shot, but really you would be doing FGE first, make it a separate relation, and then you have to
R6.
again do, because G determines G and G is not a super key of FGE, you will decompose it again into G.
Decompose, yeah, right.
And therefore FG will just become a separate.
Yeah. So first I will decompose this R2 and R5 and R6. Then I will check for again for BCNF condition, right? Here you can see I'm checking again for BCNF condition, and here FG and G is my particular decomposed relation, right?
So I'm not clear with this part. How you are getting two relations here? I was getting three relations.
Okay, tell me what you are getting.
Yeah. So R5 I took as F closure.
F closure. Okay, so that will be GE, right? FGE.
GE, yeah. And R6 I took as G closure.
G closure, okay. That will be GE, right?
And R7 as the remaining attributes, which is A and common attributes. So AEF I was getting, but I was getting three relations in this way, and options, according to options, I should get only two.
No, in option, any like one of the decomposition may be missing, right? Because we can consider this as F determine G determining as FE directly.
So you have clubbed both these according to the axioms rule and then taken F closure only.
Yeah, so we are taking F closure only here, FGE, right?
Yeah.
But for this particular relation, my G determine E will not satisfy, right? If I consider parent functional dependency.
Sorry, what?
If I consider this parent functional dependency, G determine E will not be satisfied for this particular relation R5. If I want to make this relation in BCNF. Because G determine E will be there, right?
Yeah.
Yeah, so it will not satisfy my BCNF condition.
Yeah.
Yeah.
So what will we do? Will we decompose it further?
Yeah, we can decompose.
Take R5, R6, and R7 and then solve it. Was I correct in dividing it into three relations? F
Yeah, so same thing we have done, na? Yeah. But if you consider R5 and R6, see, G is already present in the R5, na? So why you will make this separate relation? So yeah, maybe I have written a direct step here. See, you can see. So this is my R2, right? So I have decomposed this R2 into R5 and R6 first. So that will be my AEF. Sorry, AEF. AE. So it will be AEF GE, right? So I can again check. Okay. So AEF, and then I will decompose this R6 in FG. I have simply taken the closure of F here, right? FG. So, but what are the applicable functional dependency to this is F determine G and G determine E. So this will satisfy my BCNF condition, but this will not satisfy, right? So that's why I will again decompose it.
Yeah, we will decompose it again. This part is fine,
Okay.
but you have just divided it into two relations, R5 and R6. I divided it into three relations, R5, R6, R7. R7 was G closure.
Okay,
So
see, if you directly, okay, go ahead. Yeah.
Saying if R7 is a subset of R6 only. Yeah, so in that case, we don't need to divide it again. Is that what it means?
R7 is subset of R6, right? That is FGE and GE here, right?
Yeah.
Yeah.
So we don't need to divide it into R6 and R7. R6 is sufficient. Is that what it means?
No, R6. Okay, so in this question, what I am talking about BCNF condition, right? So my all the particular relation in the option should satisfy this BCNF condition. So here, if you consider FGE, so what are the applicable functional dependency here? F determine G and G determine E here, right? So it will not satisfy my BCNF condition.
Yeah, this won't satisfy the BCNF condition and then decompose it further. I agree on this, but my doubt is why have you not decomposed R7 as well? why I have just made two relations, R5 and R6, because
Sir, sorry to intervene. But I'm just wondering, I think the confusion could be this. See, what we are trying to do is in FT2, right? We have three dependencies.
Right.
So the approach I think you have taken, sir, is that we have first evaluated AE determines F is whether it's a transitive dependency or not. It's not. You're now moved on to the next dependency, which is F determines G. It is a transitive dependency, and therefore you have straight away gone ahead and decomposed it.
Straight away take the closure of this particular
of F alone, right?
F alone, yeah.
F alone, and then you've decomposed it.
Yeah. So if I take the closure of F, I will get FGE.
FGE, right?
But again, I have to check for the applicable functional dependency.
Correct. Now, I think maybe what Ria is probably trying to do is she's taken an F closure as well as G closure.
Yeah, right.
Because she's checking for both the transitive dependencies at a time.
Yeah. So here you will get three relation, FGE and GE here, right? Ria?
Correct.
Yeah. But
so that's the confusion probably.
Yeah. See, if you take the closure FG, okay, this is my BCNF condition. It is also BCNF condition. But if you observe, G is already a subset of this particular relation, right?
Yeah.
So why I will keep this in separate relation?
Okay, so that's what I was asking. If one relation is a subset of the other, we just take the bigger one, FGE. We can ignore GE because G is a subset of FGE.
Yeah, we can consider this, but if we don't want to enforce BCNF condition, but if we want our relation should be in BCNF, then we have to decompose this, right?
Yeah, we will decompose it further.
Yeah, we will decompose it further.
To R5 and R6.
Yeah,
R5 R7 because GE is a subset of FGE.
Yes. That's we have done earlier also, no? Here we have not made the separate relation. We have simply taken the closure of this attribute, right?
Okay.
Yeah.
But as a method, though, should we just take one dependency at a time, decompose it, and then evaluate further, rather than looking at all transitive dependencies in one shot? No, so what I mean is we look at only F determines G.
Yeah, only F.
Use that, decompose it, and then reevaluate all the functional dependencies, and then look at what is now violating BCNF.
Yeah. That thing also can do. Right.
Okay, it's a long step-by-step process. Maybe longer, but that's a foolproof approach. So, like if you see the options, okay. So my decomposed relation are this one: CD, ABC, AEF, FG, and GE. So if you see the option, you have any doubt in option, Ria?
No, sir. I was stuck with that last time.
Yeah.
So that rule is applicable for 2NF, 3NF, whatever decomposition we are doing, right?
Yeah. See, because like what I have done here, I just simply take one relation, try to decompose it till BCNF, right? Yeah. If you are asking about question point of view, if you can simply go through the option, you can check for this BCNF condition directly, right?
Okay.
Yeah. Because there is multiple decomposition possible.
Yeah. Right.
So I will take one practice example in that, like I have solved it in the previous session also. Okay. Sorry, I'm not sharing. Okay, let us start with the week 5 first. Okay. Yeah. Yes, Anjana. Go ahead.
Sir.
Thank you, sir. So is my screen visible? Hello, am I audible?
Yes, ma'am.
Yeah, so my screen is visible, right?
Yes.
Okay. So in week 5, we began with what are functional dependencies. Then we went further with lossless decomposition and canonical cover. So at first here we will begin with what is functional dependency. So functional dependency basically requires the value of a set of attributes to uniquely determine the value of another set of attributes. So here by definition, let R be a relational schema and X and Y are two non-empty sets of attributes in relation R. Okay. The functional dependency X determines Y holds if and only if for any legal relations R of R, whenever any two tuples T1 and T2 of R agree on the attributes X, then they also agree on the attributes Y. How? That is, if T1 tuple 1 of X is equal to tuple 2 of X, only then tuple 1 of y will be equal to tuple 2 of y. So that is the definition of functional dependency. So let us try to understand this with the help of a small example. So, okay, let me take two attributes, say x and y, and the tuples as such. 2. Okay. So here, by definition, we are asked to check that if tuple 1 of x is equals to tuple 2 of x, then tuple 1 of y should be equals to tuple 2 of y. That is when we can say that x determines y, right? So here what we will have to check in the table, what we will have to check at first is whether any two tuples are equal in the x attribute attribute or not. So as you can see that 1 out here so are equal, so we will take it as tuple 1 and we'll take it as tuple 2 of x. So we can say that yes, this particular condition is satisfying. Then we'll check for this particular condition, that is tuple 1 of y should be equals to tuple 2 of y. So here if you can see 2 and here you can see 2, right? So by that we can say that this particular condition is being satisfied. Other than that, these two tuples, if you can see, are having unique values, right? So they will obviously determine uh, the tuples on the y attribute. So by that we can say that x determines y. Okay. So now, can anybody tell whether y determines x or not? Anybody would like to volunteer?
No,
Y does not determine x.
for one value of y, the value of x changes.
Okay, can you tell which one?
In the first row, for value of y is equal to 2, the value of x is equal to 1. In the
Right.
third and fourth row, it's 3 and 5.
Oh, sorry, 3 and 1.
Acha, 1,
So-
okay.
Yeah. So for the third tuple, it is not matching, right?
And for fourth also.
Fourth, it's right, I guess, because if you can see, like, yeah, this one is not equal, but if you can see that the tuple 1 and tuple 2 are similar, right? 2, 2 and 1, 1. So they are equal. Only this particular tuple is conflicting the condition.
Ma'am, I just want to ask one thing. What is written in the last row, fourth row of x?
1 and 2.
Acha, that's
Sorry,
one.
on x it is 1.
Okay, okay. Yeah.
Okay. So by that, as you said, yes, y does not hold x. Okay. So I hope functional dependency is clear to all. We'll take one example. So here, as you can see that we have a table and we are asked which of the following functional dependencies does not hold on the given table. Okay. So we'll go option by option. So our first option is V determines Wx. Now we need to check whether this hold or not. So if you can remember from the definition, we'll check whether there are any tuples which have same values or not. So if you can see that the first tuple have the same value, second and third. So since in the definition it was only two tuples, it does not really matter how many tuples match, just that the corresponding tuple of the right hand side should also match. That is the main criteria. So this is tuple 1, say this is tuple 2 and this is tuple 3. Okay. So in the V attribute, tuple 1, tuple 2 and tuple 3 are matching, right? So we need to check whether in Wx also tuple 1, tuple 2 and tuple 3 match or not. So these are W and X. So we'll consider them as a set of attributes. So this is 9, 8, 9, 8, 9, 8. So yes, it is, so yes, that particular condition that was tuple 1 of x equals to tuple 2 of x, then tuple 2 of y equals, sorry, tuple 1 of y is equals to tuple 2 of y. So these two conditions are being satisfied. Then the leftover tuple is 9. So it is unique anyway. So it will determine. So here we can say that V determines Wx holds. Okay. So this is not the correct option because we are asked to check which does not hold, right? Okay. So we'll move to the next functional dependency, which is YZ determines X. Okay, so would anybody like to volunteer? Anyone? Whether YZ determines X holds or not?
Yes, it does.
Yeah. Yeah, please go ahead.
It does. It holds. Because
It-
each one is unique. I mean, YZ is all unique,
Yes.
even though they're determining a similar, but it's, yeah, the other way
Yeah,
around
since
is
it,
fine.
yes, right. That's correct. Since it is a set of attributes, so we won't just be seeing for one single attribute, right? So by that, we can see that all the tuples are unique in YZ. So it will obviously determine. So yes, this holds. Okay. So this is also not a correct option. So we'll check for X determines YZ. Yes. Anybody would like to volunteer? Please go ahead.
All the elements in X are same, ma'am.
Sorry?
All the elements in X are unique, ma'am.
In X, all the elements are unique. Are you sure?
888.
So they are not unique, they are same, right?
They are same, ma'am. That's
Yeah.
why they may, even though they are same, no matter it determines YZ, ma'am.
So X determines YZ or not?
YZ.
It doesn't.
It doesn't. It doesn't determine because all the values in X are same. However, all the values in YZ are unique, right? So it is not determining. So
Okay,
this
okay,
is, yeah. So this is the correct answer. Okay, so we'll check for the last option, that is WY determines Z. Anyone? WY determines Z. Anyone would like to volunteer?
It does.
Yes, ma'am, it does.
It does. Okay. Yes, that's correct. Can anybody explain why?
Ma'am, there are no repeating values in WY, so eventually it has to be.
Yes, that's right. All the values, all the tuples in the left hand side are unique, right?
Yep.
Yeah. Okay. So anybody any doubt in functional dependency? Okay. So we'll move to candidate key. So a candidate key is nothing but a set of minimal attributes that can identify each tuple uniquely in the given relation. Every candidate key is a super key, but the reverse is not true. Please remember that. Okay, so we'll try to understand how to find out candidate key with the help of an example. So this is a relational schema which consists of these attributes v, w, x, y, z, and this is a functional set, functional dependency set of the relation. We are asked to find the candidate keys. Okay, so we'll go option by option. So we have at first x, y. So we'll find out the closure of x, y, what we get when we find out the closure of x, y. So since x, y will determine itself, so x, y. Now let us check whether xy is determining any other attribute or not. So if you can see in the functional dependency set, it is not determining any other attribute, right? So xy is not a candidate key. Now let us check for wxy, the closure of wxy. So wxy will determine itself. Then if you can see wx determines z. So we will get z. Then we get yz. So yz determines v. So by that we can say, since it is determining all the attributes from the relation, so we can say wxyz is one of the candidate keys. Okay, so would anybody like to volunteer for vxy, whether it is a candidate key or not? Anyone?
It is,
yeah.
ma'am.
It is a candidate key. Can you explain? So vxy will determine itself. After that,
Then comes W. Then comes
w, because v determines w.
W, yeah, and then W and X combinedly defines Z.
Z, yeah. Yeah, so by that we can say, since all the attributes are being determined by vxy, so vxy is also a candidate key. Okay. So, okay. Anyone for vw, whether it is a candidate key or not?
It does not do anything, ma'am.
It does not, right? Because v will ultimately determine w only. So it is here only. So it won't determine any other attribute. So by that we can say that it is not a candidate key.
Ma'am, I have a question.
Yeah.
Can a primary key be a candidate key?
Can a primary key be a candidate key? Yes. it can be a candidate key.
Okay.
Primary key is a candidate key, right?
Yeah. All primary key is always
It's one of the candidate keys.
Yeah, one of the candidate.
Okay.
So, okay, any other doubts in candidate key? How to find out candidate key? Anyone?
Ma'am.
Yeah.
Ma'am, can you explain this VXY again?
Okay, VXY1, right? Okay.
Yes, ma'am.
So, VXY, we will find out the closure of VXY, right?
Yes, ma'am.
Okay. So, VXY will determine itself, right?
Yes.
So, we get VXY. Then, if you can see in the functional dependency set, V determines W. So, we will
Yes,
get W. Then, in the next functional dependency, we get WX determines Z. So, we have WX, which determines Z. So, we are getting all the attributes that are present in the relation. You got it?
Okay, ma'am. Yes, ma'am. Yes.
Okay. Okay, so we'll head to lossless joint decomposition then. So lossless joint decomposition is nothing but a relation, but a decomposition of relation R into relations R1 and R2, such that if we perform a natural join of two smaller relations, which are R1 and R2, it will return the original relation. So in order to check whether lossless joint decomposition exists or not, we must follow these three rules. All the three rules must be satisfied. So the first rule is performing the union between the decomposed relation. And when we perform the union between the decomposed relation, it must be equal to the attributes of R. That is, say for example, we have R, A, B, C, D. Okay. And we have decomposed it into R, A, B, and R1 AB, and we have decomposed it into R1 R2 CD. So when we perform a union between R1 and R2, are we getting R? Anyone? Are we getting R?
Yes, ma'am.
Yes. So we are getting R, right? Because all the values, because A, B, C, D, all the attributes in the relation are present when we perform a union between the two decomposed relation. So that is how this particular rule works out. Then the next rule, okay, sorry. Then the next rule is that when we perform an intersection between the two decomposed relation, we should not get a null value. There should be at least one common tuple. One common attribute. So can anybody tell whether R1 intersection R2 satisfies this? No, right? Because because there are no common tuples. Common attributes. Say for example, if we had C here, if we had C in the R1 relation, would this particular rule be satisfied?
Yeah.
Yeah, because
Yeah.
C is a common attribute, right?
Yes.
Yes. So this is how this particular rule works. Then the last rule is common attribute must be a key for at least one relation. So from this example, if you can see, the common attribute was C, right? So the last rule states that C should be a super key in at least one of the relation, either in R1 or in R2. Say we have a functional dependency, C determines D. So by that we can say that C determines D. So it is a super key in this particular relation, right? So by that we can say that this particular rule is also being satisfied. So the rules are clear to all, right, of lossless joint decomposition?
Yes, ma'am.
Okay. So we'll head to an example. So this is the relational schema and these are the functional dependencies set. Now we have to find out which among these options is a lossless joint decomposition. Okay. So here instead of two decomposed relations, we are having in this particular relation, we are having three decomposed relation, right? So what we will do at first is we will when we are having more than two decomposed relations, what we can do is to fulfill the first rule, we will check whether the union of all the decomposed relations are equal to R or not. So here if we can see A, B, C, D, E, F, G, H, I, and J. So yes, this particular condition is being satisfied in this option. Then we'll head to the next rule, which was performing an intersection and getting a common key, right? So here what we will do is we will like we will check for R1 and R2. Why? Because in R1 and R2, R3, because in R1 and R2 there are no common attributes, right? So at first we will check for R1 and R3. So R1 and R3. So when we perform an intersection between R1 and R3, we get I. Yes,
I.
that's right. So what we will have to check next is whether I is a super key in any of the decomposed relation or not. That is in R1 or R3, whether I is a super key or not. So if you can see out here, when we figure out the closure set of I, we get only I. So by that we can say that the third rule is not being satisfied right here only. So by that we can say that this is a lossy decomposition.
Second also not being satisfied.
The second option?
Second rule also not being satisfied. Yeah.
Second rule, we are checking it for R1 and R3, right?
Yeah, yeah.
So there is a common attribute, that is I. So the second rule is being satisfied. It is not null. Like when we will check for R1 3
and
intersection R2, then yes, then it will not be satisfied because there are no common attributes.
Yeah. In whole, it is not being satisfied. Second rule is not being satisfied for this.
Yes, that's right.
Yeah.
Second rule is not satisfied.
Yeah, yeah. Thank you.
Yeah, okay. So we'll check for the next option. So here we are having 4 relations. 4 decomposed relations. So at first we will check whether this condition is satisfied or not. A, B, C, D, E, F, G, H, I, J.
Yes,
so, yes.
ma'am, it is satisfying this.
Yes. Okay. So now can you tell which relations we will check first?
R2, R4.
Yes, that's right. R2 intersection R4. So what is the common attribute?
D.
D. Okay. So now we'll check for the third rule. So whether D is a super key in any of these 2 relations or not.
It is in R4.
Sorry?
Ma'am, D is only giving I, not J.
Why you
I and J both right?
It is true.
Yeah.
Ma'am,
So
correct,
D.
correct.
Yeah. So D is a super key. So this particular R2 and R4 satisfies the rule. So then we'll have to check for the next one. So with which we can check. So now the relations that we have is ABC, R3 will be GH, and R24 will be D, E, F, I, J. Yes. So can we check now?
No, ma'am.
No, right? Because there are no common attributes.
Yeah.
Yes,
So
ma'am.
Yeah.
It fails.
Yeah. So it fails. Exactly. The second condition does not satisfy. So by that we can say that this is also a lossy decomposition. Okay. So now we'll check for the third option. Here we have 5 relations. Okay. So would anybody like to initiate? Which sorry?
R2, R5.
R2 and R5. Okay. So the common tuples are the common attributes is D. Okay. Yeah. Then the next rule that we have to satisfy is whether D is a super key in any of these 2 relations or not.
I have a question.
It is.
Yeah. Please go ahead. Yeah.
Ma'am, the thing is, why are we starting with R1, not go in order and starting with R2 and R5?
Yeah, we can check for R1 and R2 also at first.
So no matter in which order we does, the answer doesn't change, right?
No, it won't change.
Okay, thank you.
Yeah. So now that we check, now that we get that D is the common. Sorry. Okay. So we can say that since D determines I and J, so we can say that yes, the third rule is also satisfied. So now we get R1 ABC, then R2 5 as A D E I J. Okay, then R3 as BF and R4 as FGH. Okay, so now we can check for 1 and
Yes,
R1
ma'am.
and R2 5 also. So the common attribute out here is
A.
A, right? So R1 intersection R2 5 will be
Sorry
A.
to interrupt.
Yeah.
So, ma'am, if we would have done like R2 and R5 and R1, R3 and R1 together, like at one go, so would it be valid or?
At one go, by that, what you mean? Like
So,
R2
like we
and
did for R2 and 5, right? So, can we
yes,
do R1 and R3 in the same, like same time to make it shorter?
same time, like yeah, you can do it because
In
here
the
there is a
the first
common.
step only itself, like where you did R2 and 5. So, can we do R1 and 3?
Yeah, we can do R1 and 3. Okay, would you like to initiate for R1 and 3?
Yeah, so R1 and 3, B is common, and if
Yeah, B is common. So
yeah,
is
and
B is
it is a
yeah,
super key as B gives F, and which
B
is
determines
R3.
F.
Yeah.
Yeah. Okay. So R1 and R3. Okay. So now we can convert it into R1 3, R1 3 A B C F, R2 5 A D E I J, and R4 S F G H. Okay.
Yeah.
Okay. What should we do next then?
R1 and R1 3 and R2 5.
R1 3 and R2 5. Okay. So what is the common attribute?
A.
Okay. A. R2 5 A. So is A the super key? So let's check for A closure. Okay. Yeah, please, you can volunteer. So
Yes, it is. It is a super key as A gives DE and then D gives IJ.
D gives IJ. Yeah. So by that we can say that it is a super key in this particular relation, right? So okay. So now we have
A1 2 3 5.
yes, that's right. We have R1 2 3 5, and that contains A B C D E F I J, right? And we have R4,
R4
which consists of
FGH.
okay, yeah. So what is the common attribute?
F.
Yes, that's right. The common
And F.
attribute is F.
Now
So
F
is F the
determines
super?
H.
Sorry,
Fine. Fine. Okay. Yes, it is.
it is a super key, right? Because
Yeah,
F
yeah.
determines
Yeah, yeah.
GH.
FGH. Yes, ma'am.
So
Yeah,
it is
yeah.
a super key of R4. So since we have checked for all the relations, so by that we can say that this particular is a lossless decomposition.
Lossless.
Yes.
Yes,
So
ma'am.
this is a correct answer. Okay. Just a minute. I'll just. Okay. So now we'll head to the next option. So yeah, you can volunteer, anyone. So which relation shall we? Yeah. Yeah. Anyone?
Yes, ma'am.
R2 and R1.
Yeah. Sorry.
R1 and R2.
R1 and R2. Okay. R1.
D is the common and it is a super key. Is it?
D is a super key, is it?
No, ma'am.
No, ma'am, it isn't.
D is not a super key, right? So okay, so we'll check for another relations. So
R1 and R3.
yes,
So B
R1
and B is a
intersection.
super key.
So we'll check for B. B determines F. So
Yeah.
it is a super key in R3, right?
Yes.
Okay. So now we get R1, 3. That is A, B, C, D, F. Okay. So next, what should we do?
R2, R5.
R2, R5. Okay. R2 intersection R5. The common attribute is
D.
D. Okay. So D is a super key.
Yes, ma'am.
D is a super key in R5 because of D determines IJ.
IJ.
So now we get R25. That is D, E, I, and J. And we have R4, which is F, G, and H. Okay. So what should be the next step?
R13 and R4.
R13 and R4. R13 intersection R4. So what is the common?
F.
Yeah? F.
F.
So yeah. Yeah, please go ahead. Is F a super key?
Yes, ma'am. FGH. R4.
FGH. So in R4, it is a super key.
Super key.
Yes. Yeah.
This is also.
So now we get R134. That is A, B, C, D, F,
G, H.
G, H, and we have R25. We get D, E, I, and J. Okay. Now we will perform intersection. So the common attribute out here is D. So is D a super key in any of the relation? Anyone?
No, ma'am.
No.
Why?
D is not there.
DE is not there.
ए मम्मी पानी परे छोगे पानी परे.
Okay, so it is not a super key, right, in any of the relations.
Yes, ma'am.
Yeah, so by that we can say that it is a lossy decomposition, right?
Yes, ma'am.
Yes, yes.
Okay, so any doubts in lossless decomposition, anyone?
No, ma'am.
Okay. So we'll head to dependency preserving. So a decomposition is dependency preserving if F1 union, okay. So let's say Fi be the set of dependencies of F closure that include only attributes in the relation Ri. So decomposition is dependency preserving if all the functional dependency sets, the closure of all the functional dependency set is equal to the original functional dependency. So here if you can see, let R be the original relational schema having FD set F. Let R1 and R2 having FD set F1 and F2 respectively are the decomposed subrelations of R. The decomposition of R is said to be preserving if F union F2 is equivalent to F. So then we can say that decomposition is preserving. So let us take this particular example. So here we are given a relational schema R with these attributes. So just for easier understanding, what we will do is we'll take bike name as A, bike model is B, and bike engine as C. So say suppose R satisfies the following functional dependencies. So these are the functional dependencies. So let us just convert it into A to B, B to C, and this is bike engine. So C to A. Okay. So if R is decomposed into R1, bike name and bike model. So R1, A and B, and R2, bike model and bike engine number. So it is B and C. So then the decomposition. Okay, so here we need to check whether these are lossless decomposition as well as dependency preserving or not. So let us at first check for lossless decomposition. So would anybody like to volunteer?
Yes, ma'am.
Okay, so the first rule was, so is this
union? Yes, ma'am.
So is this satisfied?
Yes, ma'am. ABC is there.
Yes, this is satisfied. So what was the next rule?
Intersection should not be null.
Right. So is that satisfied?
Yes, ma'am.
Yes, yes.
That is
B
also
is the
satisfied.
common element.
Yes, that's right. B is the common element. Then the next one was
B is the super key also.
R1 or R2. Okay, so B is a super key. B is a
Yes,
super
ma'am.
key. Yeah. Okay. So by that we can say that this particular relation is lossless.
Lossless.
Yeah. Now we need to check for dependency, whether it is dependency preserving or not. So for that, what we will do, so we have two relations, R1 AB and R2 BC. So now what we will do, we'll find out all the like functional dependency sets that we can get in this particular relation. So it will be A to say B A and B to say A B. Then here we cannot get any more any more functional dependencies in R1. So then we'll move to R2, we'll get BC, and from C we can get again CB. So no more functional dependency set in this particular relation. So here we will get say AP and here BC. Okay. So now we need to check whether the functional dependencies that we get in the decomposed relation, when we perform a union of it, are we getting the functional dependency of the original set or not? The original functional dependency set or not? So here, if you can see, A determines B, we got it here. B determines C, we got it here. C determines A is not being satisfied out here. So what we will do is, for C determines A, so from R1, sorry, from R2, what we will take? We will take C determines, even if we deduct C, it will be the same. It is just an extraneous attribute. So C determines B, and from R1, what we will take? We can take B determines A. From this, because B is, we can consider B as an extraneous attribute. Then by transitivity rule, we can say that is C to B and B to A, then C to A. So we have got all the three functional dependency sets, right? So by that we can say it is a lossless decomposition as well as a dependency preserving one. Okay. So any doubts in dependency preserving, anyone?
I didn't get this one. Like from where did you write all those below R1 and R2? Like A gives B A, B gives A B. Those.
These ones?
No, above, ma'am.
These ones?
Yes, yes.
Okay, so what we have to find out when we are getting this particular relation, decomposed relation. Now, how many functional dependency sets can we get in this particular relation? We can get A determines B, B determines A determines AB, B determines AB, right?
So here, ma'am, first we find all possible
functional dependency sets in a decomposed relation. So if you can see in here, we get B determines C, C determines B, B determines BC, C determines BC, like that.
I have a question.
Yeah.
See, if you are going to take, make combinations like these, if there are like more than 4 or 5 attributes, it can be a problem, right?
Why would it be a problem?
Ma'am, there must be a lot of, possible combinations.
Right.
And in that case, also, we have to do the same thing.
Look, we are taking these here. You can ultimately we are getting the functional dependency set that are present in the original functional dependency set, right? That is the main criteria to fulfill for a for a decomposition to be dependency preserving. So say for example, if it was only A determines B and B determines C, so we would have got it directly. We would not have required these ones, right?
Okay.
So however, we have C determines A, so we will need these ones, right?
Okay.
Yeah. So since yeah, that is how it works. We'll have to find out all the possible functional dependency set that are present in a decomposed relation.
Ma'am, then why are we not writing B determines A under R1?
R1 B, yeah, we can here look. B determines A B. Here B you can consider B is a, you can say that B determines B. It is a, you can even remove it also, right? It will still be the same.
Then why are we writing A determines B? A determines B is enough, right? Then in such like A determines A is there, so we can ignore A, and A determines B is there. So why are we again writing A determines B? So
A
it should be only
determines
two.
B, even if you write it, even if you don't write it, A determines B. If
Yeah.
you write, say for example, you are having A determines BA. So what will be the closure of A determines, what will be the closure of A? It will be A and B, right?
Yeah.
However, if you write it as A determines B only, then what will be the closure of A?
B.
No, A also determines itself, right?
Oh, sorry. Yeah, AB.
Yes. So it will be AB only.
Yeah.
So whether
Ma'am,
you, yeah.
will it not be sufficient to take the individual closures? Closure of A, closure of B.
Yeah, you can take the individual only. Like you can
Then that
simply
will be
take.
sufficient. That will
Yeah,
be
yeah,
sufficient to decide, right? No?
yeah. So you can simply take A determines B and B determines A.
Yeah.
Yeah. Since here we have only two attributes in each relation.
Okay, okay, thank you.
Yeah. So is it clear, or are you having any doubts? Anyone?
Yeah. So I think Steve asked one question, like if there is multiple attribute, right, Steve? In that case, you have to take the combination of all the attributes, like A, B,
Yeah.
C, B, C. Yeah.
Yeah. Okay. Let me show you with the help of an example.
Instead of taking just combinations, can't we do anything with the already given functional dependency list?
No,
that is what we have to find out, right?
For that, we can just compare it. No, we can just compare whatever. See, what I used to do is I will take one functional dependency and check the left hand side and the right hand side. If both of them are from a particular relation, then I will assign that a functional dependency to a particular relation. So that's how I used to solve all these days. And taking these kind of combination seems new to me.
No, when we are checking, we have to check for dependency preserving. We have to consider all the possible combination, right?
Exactly.
Yeah.
Yeah. So say for example, we have A, B, C. So we will get A, B, C, B, A, C, C, A, B. Then we will also get A, B, C, A, C, B, B, C, A. Yeah. These will be all right. A, B, A, B, A, C, B, C. Yeah. Then we will also, yeah, then ABC will determine ABC only. So these are all the possible functional dependencies of multiple attributes. So is it clear?
So our purpose is to get the F1 plus, right?
Yes, that's right. The main purpose is to get all these functional dependencies set that is present in the like parent relation.
Then only we will be able to decide the other conditions, right?
Right.
Okay, thank you.
Okay. So any more doubt, anyone in dependency preserving? Okay.
Ma'am?
Yeah.
Can you show example in which dependency is not preserving?
Dependence. Some all example, right? Okay.
Anjana, there is one example in week 6. I will take that. Yeah.
Okay. Will that be fine? There is an example regarding like where dependency is not being preserved. So sir will be taking it. Okay. Is that okay?
Yes, ma'am. Yes, ma'am.
Okay. Thank you.
Okay. Yes.
Okay. So now we'll head to canonical cover. So a canonical cover for F is a set of functional dependencies FC such that all the following properties are satisfied. So the first property is F logically implies all dependencies FC, or FC logically implies all dependencies in F. Another property is there should be no extraneous attributes in the functional dependency. So then the last one is each left side of functional dependency set in FC is unique. That is, there are no two dependencies alpha 1 determines beta 1 and alpha 2 determines beta 2 in in such that alpha 1 determines alpha 2. That is, no left hand side will have the same attribute. Like there should be unique left hand side attributes. So these are some of the rules of canonical cover. Now let us try to understand this with the help of an example. Okay, so this is the relation. These are the functional dependency set. We are asked, from among the following options, choose all the set of functional dependencies which serve as canonical covers of F on R. Okay, so here how we can proceed is, what we can do, say for example in this particular option here, what we do in canonical cover is we will remove the extraneous attribute or the extraneous functional dependency set, without which we will still get the same output, right? So in this particular first option, so say for example we are considering this particular functional dependency set, L determines Mn, Jk determines L, Km determines I. However, here we have Km determines I and Km determines N. Okay, so what we will do is we will check the closure of those functional dependence, like those, say Ik plus, Kn plus, Ikl plus, Km plus. So we'll check the closure of the left hand side ones and check whether the result is same in both the functional dependency set or not. By that, what I mean is, say for example, we'll take the, hello, am I audible?
Yes,
Yes, yes.
Okay, thank you. So we'll take the closure of Ik and let's check in the parent functional dependency set. So we get Ik determines N, then K, we are getting Kn, right? So Kn determines JL. So we get JL. So L determines Mn. N we already have, we'll get M. So Ik plus is Ik, the closure of Ik determines all the attributes. So now let us check in this particular option whether we get the same attribute or not. So Ik will determine itself. Then if you can see that there are no attributes which are being determined by Ik other than Ik, right? So we can say that this is not a proper canonical cover. Am I clear? Anyone, any doubt? Like we'll proceed with the other options also for better understanding. Whatever
so
I
we
explained.
have to find the closure, right?
Yeah, that is one easier way you can do it. Like you will have to find out the closure. If the result is similar, here you can see that when we check the closure of Ik in the parent functional dependency set and in the option that is given, we are not getting the same relation, right? Sorry, the same set of attributes, right? We are getting Ik and we are getting all the other attributes. So by that we can say that this is not a proper canonical cover. We have to only remove the extraneous attributes or extraneous functional dependency sets, right? So extraneous, as the name suggests, it means that it is an extra attribute or an extra functional dependency set. That is, even if we don't keep it, we will still get the desired output. Am I clear?
Yes.
Okay, so we'll proceed with the next options for better understanding. Okay, so our next option has L determines Mn, Jk determines L, Km determines I. Okay, so okay. So now again we'll check for Ik plus. So Ik plus, this was the closure set of Ik in the parent table. Now let us check here in the relation. So we get Ik will determine itself. Then we get Ikn. Then Kn determines J. Then we get Jk. So Jk determines L and L determines Mn, and we already have, and we get M. So here the closure of Ik is being satisfied. Okay, so even if we don't add this particular functional dependency set, we'll still get the same desired output of the closure of Ik. So now let's head to the next functional dependency set, that is the closure, we'll check for Kn, the closure of Kn. So let's check in the parent table. We get Kn, then Kn determines JL, so L determines M, then Km determines I, and Km we already have, and we already have, will get I. Okay, so it is again determining all the attributes. So now let us check for the closure of Kn in the option, in the functional dependency set given in the option. So Kn will determine itself, then Kn will determine J, then Jk we already have, it will determine L. L determines Mn, and we already have, and Km will determine I. So we have Km, it will determine I. So yes, the closure of Kn is also the same. So even like if we remove L from this particular, so here in this particular functional dependency set, L is an extraneous attribute. So even if we removed it, we are still getting the same result of the closure of Kn. Okay, so now let us check for the closure of IKL. IKL. So IKL will determine itself. Then L determines Mn. So we will have Mn. Then Km determines In. So Km, N we already have, we get Ni. So now let us check for closure of IKL in the relation. So IKL will determine itself. Then Ik determines N. Kn determines J, and jk determines L. L we already have. L determines Mn, and we already have. So yes, the closure of IKL is also same. So here, even if we don't add this particular functional dependency set, we'll still get the same result. Now let us check for Km, for the closure of Km. So the closure of Km in the parent we get, parent functional dependency set we get is Kmin, then Kn gives JL. So yeah, we're getting all the attributes. So let us check this in the relation. So Km will determine itself. Km determines I. Then Ik we have, it determines N. Then Kn we have, it determines J. So again, yes, it is. So even if we like here, N is the extraneous attribute. So even if we remove N, we'll still get the same result for the Km closure. So by that, we can say that this is a correct canonical cover. So anyone, any doubt in this, or shall we proceed?
L is not there here in
Sorry?
Km plus.
Ma'am, can you please repeat it again?
L,
From
just a
Kn.
minute.
So
L, JK, we have JK, so we get L.
Yeah.
Sorry for that mistake. Yep. Yes, somebody had some doubt. Yeah.
So for so we have to check for each and every attribute closure, right?
Yeah, you can check for each and every closure, each and every like closure set of each and every attribute also. However, you can also check for the ones which are not present in the, say this is the canonical cover in the option, right? So here there are certain functional dependency set which are present in the parent functional dependency set but not present here, right? So as I did, like Ik determines N. This particular functional dependency is not present here. So I checked for Ik closure in the parent functional dependency set as well as in this functional dependency set. So I got the same result, as you can see, right? I got both the closure set determines all the attributes. Then L determines Mn is present here. So even if we don't check, we don't need to check it because it is present here, right? Then Jk determines L, it is also present. Then Kn determines JL. So here we are having Kn determines J only, not L. So what we can do is we can also check for Kn closure. So when we check for Kn closure in the parent functional dependency set as well as in this set, we get
Ik was also present. Ik determines N was also present in both.
No, okay, yeah, it is present. Sorry, I didn't check, but even, yeah, it is still giving the same result only, right?
Okay.
Yeah,
it
so
is not required. If it is present,
it is not
it is
required.
not required.
Yeah, it was not required.
It is better to pick out the dependency which are not present.
Exactly. Right? Yes, that's right. So if you can see that Kn determines J only here, and here we have Kn determines JL, right? So here L is the extraneous attribute. That is why it has been removed. So what we will do is we'll check the closure set of Kn in both the functional dependency set. So here what we got is we got the same like set of attributes only. So by that we can say that here L is a extraneous attribute. That is why it is removed. Even if we remove L from this particular functional dependency set, a functional dependency will still get the same result. Then IKL determines J is also not present in this particular option. So we checked for the closure of IKL, if you can see here. So we checked in both the like sets. So we got the same result. After that, we had Km determines In. Here we had Km determines I. N was removed as if it was an extraneous attribute. So we checked for Km closure also. So again, we got the same same set of attributes only. So we can say that N is the extraneous attribute. That is, even if we remove N from this particular functional dependency set, we'll still get the same set of attributes for the closure of Km. So am I clear?
Yes, ma'am.
Yes, ma'am.
Ma'am, I have
Have
a
extraneous attributes in FCNA, ma'am.
Sorry?
To serve as a canonical cover, it should not have extraneous attributes.
Yeah, it should not have any extraneous attribute. So here we are removing the extraneous attributes, if you can see. Okay, it's too messy. So in these two relations, we have removed N and we have removed L from here because these were extraneous attributes. How we got to know that these are extraneous attributes? Because when we check for the closure of Kn with like determining JL, and when we like check the closure determining only J, both of them are giving the same result, right? So by that we can say that L is the extraneous attribute.
Okay.
Yeah.
Thanks.
Yeah.
I have a question.
Yeah, please go
there
ahead.
can be only one canonical form for a given set of functional dependencies, right?
No, there can be more than one. You'll see there can be more than one.
Yeah, multiple canonical cover is possible.
Yeah.
But
ma'am, here.
Yeah, please go ahead.
Please, ma'am, here L and
Yeah.
N were extraneous. L and N was extraneous. How can we ensure that others are not extraneous?
We can check the closure. Like, okay, so say for example, let us check for L determines Mn N. Okay, so let us simply let us at first take the closure of L. So the closure of L gives us L Mn, then only LMN, right? Okay.
Yeah.
So say for example, we are considering N as the extraneous attribute and we are only taking L as N. So when we take the closure of L, we get Ln. Are we getting M here?
No.
These two are not the same, right?
Yeah.
So by that we can say that M or N, both of them is not an extraneous attribute.
I got it, ma'am. Here in this where we are checking whether it is in canonical cover or not.
Yeah.
How will we ensure the others are not extraneous? Suppose we got this L is extraneous, N is extraneous. In the process of determining these closures.
Yeah, L is extraneous, N is extraneous.
Yeah. We got it here because it was extraneous. But how can we say others are not? We have to check it or not. It is required condition or not?
Like if you are getting the closure, like if you can see in this particular here, the closure of L plus was not giving the same, right? So we got to know that this is there is no extraneous attribute in this particular functional dependency.
My question is whether it is required to check all others to ensure that it is not extraneous.
Yeah, that would be better if you check.
Okay,
that would give you more precise answer.
Yeah. So in order to find the canonical cover, the first step is we have to find out the extraneous attribute.
And
remove and then we have to find out the redundant functional dependency. Okay. After removing those functional dependency, then we'll get a canonical cover. Okay. So yeah. So in a different reference book, you must have seen there is minimal cover, something like. Okay. So So what, like suppose say we have FC like A determine B and B determine C. So that we can say that is a canonical cover. But by transitivity, we can also write A determine C directly, right? So that will become the minimal cover. So we have one tutorial on this. You can watch the tutorial also. Okay?
Yeah. Okay. Awesome. Thank you.
My question. In case if there are more than one canonical cover is possible and my answer is not matching with the ones that are in the options, what should I do in that case?
Like your answer is not matching with the option.
I mean, both are at the both are canonical covers. Just that the possibility of having canonical covers is more than one for a particular given functional dependency set, and mine is not matching with the answer. What should I do in that case? I mean, I think it depends on the method we choose to solve, I guess. So the answer given will follow a particular method, and I follow a different method. Just a hypothetical case, and I got a different answer, but at the same time, it's a canonical cover, and the answer don't match. What should I do in that case?
I guess if you are having options, if you have like options like these, then you should go with the help of options only, like I am going right now.
Yeah. It is better when you eliminate whether it is yes or not.
But this can be quite time consuming. No, I have to take each and every options and solve for it. It can be quite time consuming. And if I do the same for every question, I don't think I'll have time for exam.
But in the question we are asking, like from among the following options, which one is canonical cover, right? Yeah. So if like you are right, if you are not giving any option, it's simply a like subjective question. Then you have to follow all those steps, right? Check for each and every extraneous attribute in it in every functional dependency. Try to find it out, then remove that, and then again remove the redundant functional dependency. Like say, suppose here options are not given. So in that case, what we have to do? Take ik, determine n. Check whether I or k is extraneous or not. I or k. In second functional dependency, take L, determine mn. So check whether mn is redundant or not. In third functional dependency, jk, determine L is there. So check whether j or k is extraneous or not, right?
Okay.
So in that steps we have to proceed, like.
Okay.
So would anybody like to volunteer for option 3? Like, I guess you're aware of the process now. So anyone? Yeah. Hello?
Yes, ma'am.
Yeah. So would you like to volunteer in solving whether checking whether option 3 is a canonical cover or not? So okay, let us at first check which of the functional dependency set we have in option 3 that are present in the parent functional dependency. So it is at first L determines Mn, then we have Jk determines L, then Km determines Ij. Km determines Ij. No, it's not there. Okay. So Ik determines J. So Ik determines J is also not there. So now what we will do is we'll check the closure of Ik, because Ik determines N is not present in this particular option. So let's see whether even if this functional dependency is not present, we'll get the same output or not. So IKN, KNJL, M. Okay.
H is also not present, right?
Ma'am, you are not audible.
Yeah, ma'am is not audible.
Hello, Anjana, you are not audible.
Connection lost.
Okay, you can check for the third option, right? Okay. Internet issue is there.
Sir, I have a doubt in canonical cover. Some other question.
Yes.
next question is from week 5, graded assignment question in it. So the relation given is A, B, C, D, and functional dependencies are A determines C and AB determines CD, and we need to find the extraneous attribute.
Yeah. So can we first take this example? Like we can take doubts later, right? We'll take your doubt also.
Okay.
Hello, am I audible?
Yeah, ma'am. Audible.
Okay, I'm sorry. I guess I got logged out.
Yeah.
Okay.
Screen
So,
screen is not visible.
okay, now
Okay.
is it visible?
No, visible, ma'am.
Okay. So now let us check whether the closure of IK is the same or not. So IK will determine itself. Then IK will determine J. IK determines J. Then we have JK determines L. And L determines MN. So if you can see that IK, it is the same, right? So even if we don't add IK determines N, so it will still give us the same output. Okay, so now let us check for KN closure. So KN closure will give us KNJL, then L will give us M, N is already present. KM will give us IN, so N is already present, we get I. Okay, so now let us check for KN closure in this one, in this particular set. So we get KN. Then KN is not determining any other attribute, right? If you can see.
Yes.
So by that, we don't need to proceed any further because this particular functional dependency is not present in this functional dependency. So we can say, and we are not getting the same output, right? So we can say that this particular option is not a correct option. Am I clear?
Yes,
Yes,
ma'am.
ma'am.
Only one. If only one condition is not satisfied, then we can.
Yeah, we don't need to proceed any further.
Okay.
Yeah. Okay, so would you like to volunteer for the fourth option? Anyone? This is the last
Yes, ma'am.
option. You can give it a try.
Yeah, ma'am.
Okay. Please go ahead.
So, ma'am, we can LMN is in both, so we can. mark
Okay,
it down.
LMN is in present. Okay.
JK is present.
JK determines L is present.
KMI.
But here we have KMIN, right? So we'll check for KM closure also.
Yeah. KM.
Yeah. Then
IKJ is there. And
it is no IK.
We need to
No,
check for
ma'am.
IK and
Yeah,
J.
we need to check for
IKL.
IK. Yeah.
And same for K and L.
Right. Okay. So I have not erased this one. This is the closure set of IK from the parent table. Now we'll check. Okay. Anybody would like to volunteer? IK.
So IKJ will give.
Okay. J.
JK gives L. L gives
JK.
MN.
L gives M.
MN.
Yeah. So it is same, right?
Yep.
Yeah.
Yes,
So
ma'am.
even if we don't use IK determines N and instead of it we use IK determines J, it's still the same.
Yep.
Okay. So next, what shall we check?
KN.
Okay, KN. So this is I've written already. So
No.
KN.
KN determines L.
L, yeah.
gives MN.
L gives N is already present. M.
And
Then I.
Yeah, KM determines here. KM determines I.
IK determines J.
IK determines J. So again, all the set of attributes are same. So even if we don't use KN determines JL and we simply use KN determines L, it will still give us the same set of attributes.
Right. Yeah.
Okay. Next, what shall we check?
J is extraneous here.
Exactly.
KM.
J is sorry? Okay. Do we not need to check IKL? It is
Yes,
also
we
not
need
present.
to. We need to check.
Yes, ma'am, we need to check.
Okay. So IKL will give IKL and then L will give MN and KM will give I and then KN will give JL. Okay. So I have written for the parent table. Now, would you like to volunteer for the option one?
Yes, ma'am. So IKL gives IKL and L gives MN.
L gives MN.
KM gives I.
But
K-
ma'am,
I is already there.
IKL is not in this, no?
What? In? Sorry?
IK gives J.
IK gives J. Okay.
Okay,
Okay.
Okay.
Yeah. So again, this is also same. So what would be
Yes,
the
ma'am.
next closure? Said that we
KM.
KM.
KM determinant.
Sorry. Okay, so we need to check for KM closure. So at first we
IN.
need to, yeah, please go ahead. IN,
Then JL.
JL, yeah,
Complete.
yeah. So now we need to check in the options. So KM
KM
will,
I.
okay,
J.
J,
Then L.
L,
Then MN.
M we already have, we will get
N.
N. So now we have finally figured out for all the set of attributes, right? So by that we can say that this is also a canonical cover, right?
Yes, ma'am.
Yeah. Okay. So canonical cover is clear to all, right?
Yes,
I
ma'am.
have a doubt in some other
Yeah.
question related to extraneous variables.
Okay. What
Yeah.
can you tell me the question number?
Yeah, week 5, grade assignment question 8.
Yes, sir. Yeah, we'll take that question. And then how many questions are remaining?
So it's done, sir. Canonical cover was the last one.
Okay, okay. Okay, I will take that.
Okay, sir.
I have doubt in question 1.
Sorry? Hello? Yes?
I have doubt in question 1 of the PDF which ma'am is showing.
Just 1 minute. Yeah, we'll take one by one. Yeah. So question number 8, right? Week 5, Ria.
Yes, sir.
Yeah, so here we have to find out the extraneous attribute, right?
Yes. So can I tell my approach first and then you can point out where I'm going wrong?
Yeah, okay. Let's first tell you what is extraneous attribute.
A variable, even if we remove that from the functional dependency, we get the original function.
Yeah. Even if we remove those attributes, we'll get function dependency will not get affected, right? Yeah. So okay, tell me your approach.
Yeah, so first I split CD. So I wrote it as A function determines C, AB determines C, and AB determines D. Yeah. Then in the first two dependencies, since A determines C by itself and B is extraneous.
Right. Yeah.
Yeah. So we can remove B, right? It won't affect the functional dependency even if we remove B. So B is extraneous.
How? No. See. Okay, so like if you are checking for left hand side, right? Yeah. So we can split like this: A determines C, AB determines C, and AB determines D.
Yes.
Right. Yeah. So this.
So from the first functional dependency, we have A determines C. And in the second, we are writing A, B determines C. So A is sufficient to determine C, right? So B is extraneous there. We don't need to write B.
How? So AB is combinedly determining C, na?
Yeah, but A can also determine C by itself. So A along with any other attribute can also determine C. A, B, D can also determine C.
Yeah, see, here we are checking for this functional dependency, right? So first thing is that whether A is extraneous or not, right? And second thing is that whether B is extraneous or not, right?
Yeah.
Yeah. So if you are, yeah. So here what you will do, okay. So at first we'll check whether A is extraneous or not. So I will remove A. Okay, I will skip this A. So if I take the closure of B, am I getting CD? The closure of B is getting CD or not here? No, right?
No.
Yeah. So let us check for B now. Now just remove B from this functional dependency. Now if I take the closure of A, will I get CD?
No.
I am getting C only. Yeah. So D, I will not get D, right? So this is not an extraneous attribute.
But
Now let us.
split it.
Yeah. So you have split this, right?
Yeah.
Yeah. Now suppose if I want to check on right hand side of this functional dependency. So what I will get, like A determines C. Yeah. So if I take the closure of AB, I will get ABC, right? So I can say AB determine C also here.
Yeah.
Yeah, because by using this. So C is an extraneous, right? Even if I remove C, even if I get the closure of AB, still I will get C, right? By this functional dependency. Yeah. So even if I remove D here, so will I get D in the closure of AB? No, right? So D is not an extraneous here.
But sir, you are taking CD together. What I did was I split it. So I took AB determines C and AB determines D. So in that case, B was coming extraneous. If I split it, so RHS will contain only one element, right? So we don't need to check it on RHS as such. We just need to check it on LHS.
Yeah, see, if we want to check on the left hand side, do we need to split this?
I split it because we can, right? It's a rule. So I simplified it first.
No. So what do you mean? Okay, here B is extraneous, right? So what will be my canonical cover then for this functional dependency? A determines C and AB determines D, right?
Yeah.
Sir, AB determines C, B is not extraneous. AB determines C itself is a redundant relation. Redundant dependency.
We need to tell the extraneous variable, not the redundant variable.
Hello.
So what I'm saying is AB determines C itself is not required. I mean, it's redundant dependency.
Yeah,
because
it's not that's not a part of canonical cover, but we need to tell the attribute that is extraneous.
Hello.
So
Piyush sir, am I audible?
Yes, Pradeep.
Yeah, I want to add something. So, who asked that question, Rhea? So, Rhea, what approach you decompose first, right? So, in that way, you got the functional dependency, whichever is the redundant functional dependency. So, your question is you have to find the extraneous attribute. So, to match the extraneous attribute, first you have to make the left side unique. All the value of the left side means A to C, right? A to C and AB, you have to make unique. If it is decomposed, make it union, right?
Okay.
So you're talking about the algorithm, right? That union is
Yeah. So what is the confusion in that way? You make the decomposition, right? So AB decompose C and AB decompose D, right? And in that way, you got the AB to C is the extraneous. So that is the extraneous functional dependency. Means redundant functional dependency, right? But you have asked what is the extraneous attribute. Hello?
Yeah, I asked the extraneous attribute. So, so after decomposition, what I got was A determines C, AB determines C, AB determines D. Okay. So we know that A determines C by itself. So AB would also determine C. So B is an extra variable here in AB determines C, because we have already seen that A determines C. It does not need any other variable. So B is extraneous variable.
Yeah. So if you remove B, so shall I get A determines CD? Will I get A determines CD? No, right? I will only get A determines C. What about this D? right? So that is what extraneous. Now, if we remove the particular attribute, it should not affect the parent functional dependency, right?
So how will we retain D if we remove C? And we also show that.
Yeah. So in this case, okay. So here we don't need to check because there are only single attributes are there on both the sides, right? So here we have to check whether A or B is there. So in left hand side, what we will do? Just for checking whether B is extraneous or not, just take the closure of A. If we are getting B in that A closure, then we can say that B is extraneous here. For A, just take the closure of B. If we are getting A in the closure of A, then we can say A is an extraneous. Okay. Now on left hand side, we want to check whether C is extraneous or not, right? So just keep C, take the closure of AB. So will I get ABC here? Like here you can see, right? From A, I can get C. So I'm already getting an ABCD here. So I'm getting the C here if I take the closure of AB. So C is extraneous. Now what about D? So if I skip this D, will I get D in AB closure? No, it will be ABC only, right? So C is the right option here. Yeah. So just go to the definition, like you have to only tell, right? So extraneous attribute are those attributes if we remove from the functional dependency, it should not affect our parent functional dependency. Yeah. So yeah, I think yeah. So earlier we are discussing one doubt. Just 1 minute. Okay, so these are the questions from the mock test we will be discussing. But before that, I want to take one example. Okay, so suppose I have relation R, A, B, C, D, E, and I have functional dependency as A determine B and and BC determine D. Okay. So okay, and we have to check for BCNF decomposition. Check for, or we have to decompose this into BCNF. Okay. So yeah. So what? Okay. So earlier Ria was there, right? And Kaushik is here.
Yes, sir.
Yeah. And Piyush. Yeah. So what Ria will do? Okay. So first we have to find out the candidate key. Okay. So what will be the candidate key here? ACE must be a part of candidate key. So if I take the closure of ACE, I will get all the attributes in the relation R. So ACE is the candidate key here. So whether this A determine B is violating my 2NF condition. Hello, anyone?
2NF, yes.
Yes, so it's violating my 2NF condition, as well as if it's violating 2NF, it means violating BCNF condition also, right? Yeah. Whether this BC determined is violating my 2NF condition. This is non-prime attribute plus prime attribute determining non-prime attribute, right? This doubt you have asked earlier, right?
Yes, yes.
Yeah. So this is also partial dependency.
Right.
Yeah. So now I have to remove this partial dependency in order to make the relation in 2NF. Okay. So what Ria will do? Ria will take the first functional dependency A and then take this closure. So closure of A will be AB. So this will be my relation R1. Now, in order to make this decomposed relation lossless, what she will do? She will add R2 as remaining attribute. That is C, D, E. Now, if I want to make this decompose lossless, what attribute I have to add? A or B? A here, right?
A,
yeah. So it will be my R2. Now let us check for the functional dependency applicable to this. So it will be A determine B, right? And it will be for this FD2. Is there any functional dependency applicable to this relation R2?
BC determines D.
No, D.
No.
C, D is not present, right?
No, yeah.
No. So what Ria was saying earlier, say I have A determine B and B determine C. So I can write A determine C in this decomposed relation. Now what I am saying here, by pseudo transitivity rule, say suppose A determine B and B determine C, it is there. So can I write A, C determine D by pseudo transitivity rule? Hello, anyone?
Yes,
Yeah.
sir.
Yeah.
Yeah. So this functional dependence is applicable to this R2, right? Hello.
Correct. Correct.
Yes, sir.
But if you observe this, AC is a subset of candidate key and D is a non-prime attribute, right? So this is also partial dependency, na?
Right.
Right. So in order to remove this partial dependency, I have to again decompose this relation. So what I will do, I will simply take the closure of AC, that is ACD. Yes, it will be R3. And what are we R4? ACD is over. E should be there, and AC should be there, right? So this will be my R4, right? So my 3, okay. So this is already in BCNF. R1.
Yes, so we will decompose it into R3 and R4. But
Yeah.
if we don't take the pseudo-transitivity rule, then FD of R2 won't have any element because parent functional dependency does not have any such dependencies. So here pseudo-transitivity is necessary, right?
Yeah. If you, so transitivity means what? Yeah. So like if I argument by C, like argument will give me AC, BC, right? And from BC I will get D, right?
Yeah.
So
So
this
here
will,
we have to do it.
yeah.
Otherwise, we will get a 5 set for functional dependency of R2.
Yeah. Right. Yeah. So these 3 are my BCNF decomposition, right? Hello. Till here you got, right?
Yes, sir.
Now, okay. So now what Kaushik will do? So instead of taking AB first, he will consider BC determine D. Okay. Because initially Rihas considered only this functional dependency, right? Because both the functional dependency is violating my condition, right? So if I take the closure of BC,
Actually, what I would have done is I would have taken R1 as A closure, R2 as BC closure, and R3 as limit.
Yes, so that is what we have to do. Yes, right. That is what we have to do. Yes. I will come to that also. Yeah. So what Kaushik will do, take the taking the closure of BC. So we'll get BCD. So I will consider this relation as R1. So what should be my R2? A, E should be there, and BC, right? In order to make a lossless decomposition, I have to add BC, right? Hello?
Yes, sir.
Yeah. So here FD1 will be BC determine D. And here FD2 will be, here you can see A determine B is applicable, right? But my key for this relation is what? ACE. Yeah. So it will violate my 2NF condition. So I will again decompose this R2 into R4, R3 and R4. Okay. So R3 and R4. I will simply take the closure of A, that will be AB. Now what are the remaining? EC should be there and A should be there, right? So what I get? I got BCD, AB and ACE. So this is another BCNF decomposition possible. Earlier what we get? BCD, ACD and EAC. So AEC and no, sorry, not BCD, that is AB. So AB and AEC is common. Only ACD and BCD is different, right? So my both the decomposition, okay. So decomposition what we have got, that is R1 is AB, R2 is ACD, R3 is AEC. What Kaushik got, R1 is BCD, R2 is AB, and R3 is AEC. Right. Now what Piyush will do? Piyush is okay. So these two functional dependencies are violating my 2NF condition. So I will take the closure of both the functional dependency. So A closure, I will make it as AB. I will take BC closure, I will make it at BCD, right? But if you observe, this decomposition is my lossy, right? If I take the intersection of R1 and R2, I will not get the original relation R because B is common here, right? If I take the closure of B, I will not get R1 and R2. So in order to make this decomposition lossless, I will add one relation R3, and that will be my candidate key, that is AC. Now, if you observe this R1, R2, R3, it is a lossless also and dependency preserving also. And I am getting the same as that Kaushik got, right? BCD, AB, ACE. Now, what I want to say that, okay, so these two are the possible BCNF decomposition. This is also BCNF and this is also BCNF. But whether this my functional dependency BC determined D is preserved in the relation in the first case, because here you can see BCD is also preserved and AB is also preserved. But in this first decomposition, BC determined D is not preserved, right? You can see BCD is not present in any of the relation, right? So if you check for dependency preserving, this BC determined D will not be preserved. Even if this three relations are in BCNF, but this dependency will not preserve. So this is the case of relation R is in BCNF, but not dependency preserving. In second case, it is R is in BCNF, but dependency preserving. Like we have to check, take the closure of F1, F2, F3, union it all, and check whether this BCD are getting us or not. But yeah, if you do that, we will not get this dependency. You can try it out. Okay, check whether we are getting the BC determined D if I take the closure of this. So what I want to say, okay, even if you decompose this relation into BCNF, there can be two ways. It can be BCNF, but not be dependency preserving. It will be a dependency preserving. It will be BCNF, but also can be dependency preserved, right? Okay. Any doubt, like what I want to say?
So then, which means, see, between step one, method one and method two, that really is determined based on which dependency I took first, whether it was A, B first or B, C, D first. But the real approach would be number 3 only, right? So we have to take number 3 is the approach then.
So whether it's 2NF or 3NF, check for all the dependencies which is violating, which are the partial dependency. So in this case, both the dependency are partial dependency, right? So I will take the closure of both the left-hand side of both the functional dependency. Even if there is one more functional dependency, say A, C determine D, it is also a partial dependency, then I will again take the closure of AC. Okay. So whatever the functional dependencies are violating my condition, just simply take the closure of the left-hand side of attribute and make them relation R. That is the third method that we have followed, right?
Right.
Yeah.
Yes, sir. And sir, if one closure is a subset of the other, then we can ignore the subset one and take the bigger one.
Yeah. So like, yeah, earlier what you have said that we are getting FGE and GE, right? But this is also violating my BCNF condition. Then I'll again decompose this into F and GE. But I'm already getting GE here, right?
Yes.
Yeah, so no need to write 2 times, right? You can simply write FG or GE. Yeah. So now we'll move on to okay, any doubt in this part? I will not discuss this example. This is a practice assignment question. I already discussed this in the week 6 open session. Here I also done the same thing. Like I have decomposed this, like I have taken the closure of 2 functional dependencies which are violating my 2NF condition, and I have added the third relation, that is my candidate key. Okay, so you can try it out, or you can watch the week 6 open session. At the beginning only I have discussed that. Okay, so now this type of question that we have discussed just now. Yeah, so this is my relation R and this is my functional dependency. Okay, so here we need to check, like R can be decomposed into BCNF and all dependency preserved, and R is decomposed into BCNF and all dependency cannot be preserved. So in this type of question, we need to check for all the possibilities. We need to be careful little, right? So, okay, anyone would like to volunteer? Like, how should we approach?
So we can start with first left-hand side of all the functional dependencies and see if there are super keys.
Yeah, so if I start, what is my P is there, M is there, P, M, Q, N, O, Q, N, O. Okay, so all the attributes are present on the left-hand side of functional dependency, right? So in that case, what I have to do, just simply take the closure of all the attribute M, N, O, P, Q. Okay, so I will also tell how to do that. Okay, so if I take the closure of M, what I will get? M, N, O. From N, I will get P. From OP, I will get Q. So I am getting all the relations present, so all the attributes present in the relation R. What should be my closure of N plus NP, right?
Yes, sir.
Okay. O plus?
Nothing, sir. Just O.
O. Okay. Closure of P?
Just P, sir.
Just P. Closure of Q?
M and NO.
Okay.
M, NO, P.
Yeah, see, if I take the closure of Q, I am getting M here. But from M, I can get all the attributes in the relation R, right?
Right.
So Q is also candidate key. So here M and Q are my candidate key. But if I take the combination of this candidate key with any other attribute, I will get the same relation R. So it will be my super key. Okay. So what are the attributes remaining? N, O, P. So here we have to check the combination of NO, NP, and OP also, right? Because we have to check for all the possible combination. Why we are not considering M and Q? Because if we take the combination of any other attribute with the candidate key, it will be a super key, right?
Yes, sir.
Yeah. So that's why we are not considering M and Q. So that is N, P, and NO. Now take the closure of NO. From N, I will get P. O will be there. From OP, I will get Q. And if I get Q, it will give me all the relation, right? R. Just take the closure of NP, what I will get? From NP, no, right? Only NP will be there. If I take the closure of OP, from OP I will get Q, and from Q I will get all the attributes present in the relation R, right? So this will be my. So here we have 4 candidate keys, that is M, Q, NO, and OP. Any other possible combination is there? For that we need to check. Anyone? Combination of 3 attribute or 4 attribute. M is done, Q is done, N is done, O, P, Q. Oh, Q, no. Okay, that this is, yeah. If you take the any other combination, you will get it will be a super key, not a candidate key. So these 4 are my candidate key. Okay. So now see which of the following, which of the functional dependencies violating 2NF or 3NF condition? Partial dependency and transitive dependency here. Yes, anyone?
So the first option will be eliminated.
Yeah. So see whether this relation is R in BCNF. What is the condition for BCNF? Left hand side must be a super key, right?
Yes.
So here you can see N is not just violating. This is okay. This is also okay. Okay. So okay. So N determine P is violating my BCNF condition, right? Yeah. So this is not correct. So if R is decomposed into 3NF but not BCNF, then all the dependencies of R cannot be preserved. Now check what is the 3NF condition here.
So either left hand side has to be super key or right hand side has to be a part of prime attributes.
Or okay, so say suppose left hand side and determine the right hand side, and it must be a prime attribute. Or I can say non-prime attribute determining non-prime attribute, right? So check for 3NF condition here. Already my 3NF condition here. This is my super key, this is also my super key, and OP is also my super key, right? So this N determining P. Okay, so it is validating my BCNF condition, sorry, 3NF condition. Both are prime attribute, right? Hello?
Yes, sir. Yes. Yes.
Yeah, so it is not validating my BCNF condition, right? So this relation already is in 3NF, right?
Yeah.
Yeah. So this is also not correct because all the dependencies are preserved here, or you can see. Now we have to decompose this relation R into BCNF and check whether the dependence is preserved or not. So how to do this? So which condition is validating my BCNF condition? Here. This is a left hand side is a super key, left hand side is a super key, left hand side is a super key. So only I have this particular function dependency where left hand side is not a super key, right? For BCNF. So what I will do, I will simply take the closure of N, right? I decompose it into N plus. So what will be N plus here? And determine P only. Hello?
Yes, sir. Yes.
Yeah. So, okay, any other? No. So this will be my R1. So what should be my R2 here?
The rest of the attributes.
So M and O. So which attribute I have to add? N here. No, N should not be there. Right. And P is there. Then M O Q. Okay. In order to make lossless, I have to add N here, right? So this will be my R2. Now, okay, for this relation R1, what are the applicable functional dependency? N determine P. For this relation R2, what is the applicable functional dependency? Q determine M. M determine NO, right?
Yeah.
OP determining Q is not applicable because P is not there, right? So both the relation are in BCNF, but OP determine Q is not preserved. So we have to check whether this OP determine Q is preserving or not. So how to do that? So let us check F1 plus closure. What I will get? If I take the closure of N, I will get NP only. So I can say N determine P here. So if I take the closure of P, will I get N? No. Now let us take the closure of F2 plus here. See here, M and Q are my candidate key. So if I take the closure of M, I will get all the attributes, right? That is O, Q, N. Similarly for Q also, I will get O, M, N. Right? Are you getting it? Hello?
Yes, sir. Yes. Yes.
Yeah. So M and Q are done. So what is remaining? ON. ON is also a candidate key here, right? So from ON, I will get all the attribute that is M and Q, right? I will get all the attribute, but I can write ON determining MQ, right? Now, if I do F1 plus union F2 plus equals to F plus, now from F plus, will I get OP determine Q? Let us take the closure of OP. So, no, I will not get OP, right? I will get only OP. So this my functional dependency is not preserved. So my answer will be option D. R is decomposed into BCNF, then all the dependency on R cannot be preserved. Hello? Yeah. Any doubt in this question?
No, sir.
Yeah. Like in the previous example, I have took like instead of R, there is A, B, C, D, E. And instead of those functional dependency, they said there is A determine B and B, C determine D. Now in that case, what will be the correct option? This both, right? We can decompose into BCNF such that dependencies are preserved. We can decompose into BCNF also such that dependencies are not preserved. It is MSQ question, right? Are you getting it? What I'm trying to say?
Yes, sir.
Yeah.
Sir, in that question, in that example where you had found the pseudo transitivity, that is really just F2 plus, right? That's what we are trying to do. We are calculating F2 plus.
F2 plus here.
Yeah, FD2 plus is what is giving you AC determines D. No, in the first approach, in that one, AC determines D you've got, no, from pseudo transitivity. So that is FD2 plus, right?
Yeah, from FD2 plus I will get AC determinant D.
Okay, so for every decomposition, we are really also calculating the pseudo transfer. We are calculating FD2 plus.
See, that we have to see. Like if there is only one dependency that is validating my condition, then we no need to check for that.
Okay.
But here you can see, like AC determinant D by pseudo transitivity. If you consider to follow this method one, we need to check. So best way is to find out which of the functional dependencies validating my partial dependency, and simply take the closure of all those attributes, left hand side of the attribute. Make them as a relation R1, R2.
Okay.
And if the decomposition is not lossless, then you can add third relation as a candidate key. Okay. So this example I have already explained. You can try out this example. So here ABH, I think this is the correct one. So in that the session what I have taken another candidate key, that is ABC. Okay. So there are two candidate key possible here. So in this option, only one candidate key is used. So in that session, I have took another candidate key, but the option answer will be the same. Okay. Yeah. So I think okay. So I think this is an easy question from MOOC. You can all answer. Like for lossless, it must be R1 should be equal to R1 natural than R2, and yeah. So here you can see if these two conditions are satisfying, then decomposition is lossless. Okay. So any doubt in normalization part, that is 1NF, 2NF, 3NF, BCNF? Right. So this is the question based on multi-valued dependency, that is 4NF thing, right? Anyone tried this question? Anyone of you? This is a mock question, right? No one has tried this question.
No, I tried, but I mean, a little bit of trial and error is what I found. I mean, I couldn't. I mean, I understand multi-valued dependencies. The rule of it I understood, but when it is written as A multi-determines B and B multi-determines D, then finding the answer was a little. I found it. I mean, I eventually found it, but then I didn't have a method to do it.
Yeah. So in the relation R, both the MVD must be there, right? So that's what this question is saying. If the following dependencies are there. So yeah. So how to approach this question? Anyone tried? A, B, let us take the red. So A, B, C, D. Okay, so what are the conditions for MVD? Like if T1 alpha equals to T2 alpha, then there must exist. There are four conditions, right? What are the four conditions? First one is T1 alpha equals to T2 alpha equals to T3 alpha equals to T4 alpha, right? What is the second condition? T1 beta equals to T3 beta and T2 beta equals to T4 beta. So what is alpha and beta here? Like alpha multi-determine beta. So if this MVD exists in the relation R, they should exist. It should satisfy this condition, right? So what are the other conditions? T1 R minus beta equals to T4 R minus beta, right? And T2 R minus beta equals to T4 R minus beta. So you should remember this condition.
T3,
okay?
T3, right? T2 R minus beta.
T3 R minus beta. So you should remember this condition. Okay. Now simply apply this. A determine D. Okay. So we have given these two tuples, right? So it will be 0, 1, 2, 3, 4. 0, 5, 6, 7, 8. So I'll consider this as T1, this one as T2. Now, what is my definition if T1 alpha equals to T2 alpha is there? So let us consider this A determine B first. So T1 alpha equals to T2 alpha, right? So then there exists this satisfy it should satisfy this 4 condition. So if you apply this 4 condition, what should be my 3, 3 and 3, 4? Now looking at the first condition, it should be 0, 0, right?
0, 0 and 5 and 1.
Yeah, here T1 beta, T3 beta. So T1, T3, that is 5, 1. And here T1 R minus beta equals to T4 R minus beta. So T4, it is 2, 3, 4 and 6, 7, 8, right? Now if you observe, it will satisfy my this for this only A multi determine B only. So here I'm getting the 4 tuple. Okay, so I will erase this now. Okay, so till now any doubt, anyone?
It's clear.
Yeah. So now we have to check for B multi determine D. It should also satisfy, right? B multi determine D. So according to definition, there are 2 possibilities, right? T1.
What do you do in the last step? Just immediately. So
like
2, 3, 4 and 6, 7, 8.
Yeah, T1 R minus beta equals to T4 R minus beta. No? So T1 R minus beta is 2, 3, 4 CDE. So it should be 2, 3, 4, right?
Okay.
Yeah.
Good.
So now in order to satisfy this MVD, B multi determine D, what is my condition? If there exists 2 tuples such that T1 alpha equals to T2 alpha, then there exists those 4 conditions, right? So in this case, I have 2 alpha value, that is 1 and 5. Hello?
Yes, sir.
Yes, sir.
So what I will do, it will be, wait. I will write A, B, C, D, E, and I will write A, B, C, D, E. So here 0, I will consider 1 first. 1, 2, 3, 4, 0, 1, 6, 7, 8. So here 0, 5, 6, 7, 8, 0, 5, 2, 3, 4. Okay. Okay, so are you getting it what I am doing here? I have split this table into 2 tables, right? Because I have to satisfy this condition. Na? T1 alpha equals to T2 alpha, right? In this case, my alpha is B, right? This is my alpha and this is my beta. Hello?
Yes, sir.
Yeah, so now I will apply those 4 conditions to both the table. So it will be 0, 0, like, oh no, 0, 0, sorry. So B multi determine D. So alpha, T1 alpha equals to T2 alpha equals to T3 equals to T4 alpha. So alpha is beta. So B here. So 1, 1, right? Now what should be D? T1 beta equals to T3 beta, na? T3 beta. So my beta is D here. So D will be 3 and 7, right? I'm just applying those 4 conditions. Yeah. So what is my other condition? T2 R minus beta equals to T3, na? T3 R minus beta.
How did you get this 3 and 7, sir? Beta?
No, just apply those 4 conditions. I have one more condition, that is T1 beta equals to T3 beta. So this is my T1, this is my T2, this is my T3. So our beta is D here in this case, right? So T3 beta must be equals to T1 beta, right? This 3, right? So T1 beta must be equals to T3 beta, right? And T2 beta must be equals to T4 beta, right?
Yeah.
So that's why 7. So now other condition is T2 R minus beta equals to T3 R minus beta. So T3 R minus beta will be 0. Sorry, T2,
0,
right?
1, 6, 8.
0, 1, 6, and this one is 8. And here will be 0, 2, 4, right? Now same thing we have to apply for this table also, because for this also this condition is satisfying. Then there should exist those 4 conditions. Now I will directly write it here. That is 5, 5. It will be 7, 3, right? Again.
7, 3. Yeah, 7, 3.
7, 3. 7, 3. Now this one is 0, 0 and T2, T3.
0, 5, 6, 7, 8.
2, 4 and 6, 8, right?
Correct.
Now if you observe, how many tuples are there in total?
8.
Yeah, because these two and these two are the tuples from this only, right? So this is my 4 tuple, this is my 4 tuple. So in total, I will get 8 tuples such that both the MVD will satisfy. Okay, now just take the option 0, 1, 2, 7, 8 is present. 0, 1, 2, 7, 8 is not present. So this is not correct. 0, 5, 6, 3, 8 is present. 0, 5, 6, 3, 8. This one is present. This is now correct option. 0, 1, 6, 7, 8 is present. 0, 1, 6, 7, 8 is present. So this one is my correct option. 0, 1, 6, 3, 4 is present. 0, 1, 6, 3, 8 is there. No, it is not present. So B and C will be my correct option.
But this doesn't cover all the additional tuples we need to add, right? It's just saying only 2 are available of the things that we need to add actually to make it multivalued. So what I'm saying is they have given 2 tuples. We have added 6 more tuples.
Yeah.
We have added 6 more tuples to find
tuples.
To make it multivalued, of which only 2 we are saying is present in that 6. So that's
no, in this question, which of the following tuples must also be in the R, right?
Must also be in R. So that's okay. So I kind of confused it as what are the other? I thought only 2 more tuples had to be added to make it multivalued dependency.
In total, there should be 8 tuples. So we have to add 6 more tuples. So out of 6, 2 are present here.
Okay.
It can be possible, like in MSQ question, we can give all the 4 options where all the tuples are possible, right?
Right.
Okay. Okay. Any doubt in this part?
So, sir, if the first element of both the tuples are different, then how will we split it?
Sorry, the first element of?
We have 0, 0 here, right, in the tuple position. So let's say we have 1 and 0.
Then there is no MVD, no? For MVD, there should exist T1 alpha equals to T2 alpha, right? If we have alpha multi-determined B and we have A, B, C, so 1 must be equals to 1. So T1 alpha must be equals to T2 alpha. If this is not true, then we no need to check for the further condition, right? It is not an MVD.
Okay.
Yeah. Okay, I hope it's clear to everyone. So in this week, we have discussed about the normalization. So 1NF, no multivalued attribute. 2NF, no partial dependency, means if a subset of candidate key is determining non-prime attribute. Then 3NF, no transitive dependency, means NPA, non-prime attribute determining non-prime attribute. This is not allowed. This is also not allowed. And BCNF, left-hand side must be a key. And 4NF, there should be no multi-valued dependency. Okay. So if the relation is in 4NF, it must be BCNF, 3NF, 2NF, as well as 1NF. Okay. So this is in week 6. In the week 7, I guess most of the theoretical part is there. You can go through the slides. Yes, Pradeep, any question in week 7? Okay, any doubt? Anyone in week 7? Yes.
Yeah. Hello, everyone. So any doubt in the week 7? So most of the part of the week 7 is the theoretical part. The important part is the 7.4, where you can see the using the Python. So you have to access the database, right? So there are several processes of that. So like first you have to create connections, then create cursor, and then executes the query, and then close the you either want to commit the connection or the rollback, that whatever you have execute in the database, the SQL query, then close the cursor and then close the connection. So these are the 6 important steps in this Python database connectivity. Okay. So any other doubt in the week 7 you can ask, or we can move to the week 8 content.
just one, like a couple of questions. So there was one on which says entire architecture or the entire architecture, whether GUI is included or not, web server is included or not, application server is included or not. So I think there was one question where we had to tick which ones are excluded or not part of the entire architecture. I had chosen web server, but I mean, the answer is wrong apparently because it's GUI which is not included in the web application architecture. So I just wanted to know, isn't GUI a part of a tier?
No, can you specify which of the question? So
okay,
it will be better.
I have to look for it. Okay.
It is in graded question, right? Week 7.
That's
Sir,
correct.
it's in graded question.
Yeah. So we have re-evaluated. We are not considering that question. GUI is also a part of the.
Okay. That's what. Yeah. That's my. Okay.
The question number 7, right? 3-layer web architecture.
That's right.
So you can see we have awarded 0 points to that question. Yeah. Okay. All the options are correct here. Yeah.
Right. Or even web server is part of the tier, one of the tiers, right?
Yeah.
Okay. And similarly, CGI, I think I had posted in this course also. CGI is an interface between the web server and the app server, the common gateway interface.
Yeah. So app server, it is the common gateway interface. So it is the interface between the web server and the whatever program you want to run on the server side, right? So it acts as app server. So it is like the interface between that. So suppose your web server is want to run some database server. Suppose the database server, database server. So that's the CGI is coming to the picture. So it is the interface between web server and the data server.
Okay. Thank you.
Yeah. Subhendu, we can move to the week 8 content.
Okay. My screen is visible?
Yes, sir.
Hello. Okay.
Yes, sir.
Okay. So we'll discuss important topic with the help of questions. So in week 8, BST is the important topics. So I would like to ask one questions. What is the RT of the BST tree? Anyone? RT of BST?
Number of child.
Maximum number of child.
Yeah. So what is the RT of BST?
Total number of.
Anyone?
Child attributes.
So RT of BST will be 2, right?
Yes, sir.
Okay. So So in this example, consider the binary search tree shown in figure 2. Which of the following is the correct insertion order which will result in the given BST? So let us insert option nodes in the BST. So 64, then 31 is less than, right?
Yes.
31 is less than 31. Then 20 also less than. Then 52 less than but greater than 31, 52. Then 10 is less than 20, right? Then 96 greater than 64, 96, right? Then 98 greater than 64, greater than 96, greater than 96, 98, right? Then 69, right? So greater than 64 but less than 69. You can see that here is 79 but here is 69. So this is the not correct option. This is the wrong option, right? Let's see second option. Let insert 64, right? Then 31 is less than 64, 31, then 20, then 20, right? Then 20, then 52. It's less than 64 but greater than 31, 52. Then 10, insert 10, insert 10, less than 20, right? Insert 96, insert 96, it is greater than 64. Then insert 25, less than 64, less than 31, but greater than 20, 25, right? Then insert 79, 64, but less than 96, so insert 79. Then 84, greater than 64 but less than 96, but greater than 79. Then 84, right? Then 98, so, and 69, right? So we can see that this is the correct answer, this and these are the matches, so this is the correct answer. You can insert like this option 3 also, right? So any doubt in this question?
When we put 69 here,
yeah,
when it is greater than this and less than the intermediate values, then what is the rule to fix?
Yeah, okay. When you insert 69, it's greater than 64, right?
Yeah.
Hello. Then move to the right. It is less than 96, right?
Yeah.
So it moved to the left. It less than 69, 79.
Yeah.
So move to the 69. Right, like this.
Okay. Why we can't put 84, 69 attached to the 84?
Which 34 means?
Yeah. 84.
84. Yeah. See, in the BST, you know that the left subtree is less than the root node and the right subtree it is greater than the root node. If you insert,
got it.
If you insert,
got it.
If you insert, okay, thanks. Any doubt?
Thank you. No, thank you. This was the doubt.
Oh, okay. So we'll move to the next question. Okay. So consider a disk having 128 track per surface, 5112 sector per track, and 256 bytes per sector. If the minimum numbers of bits required to access a sector is 21, find out the numbers of letters is required, right? So this is the questions. So anyone how to solve? Okay, let me solve. Total numbers of sector will be numbers of sectors.
28 into 512.
Kilo numbers of recording surface. Surface into 128 into 5112, right? This will be the, so you know that total numbers of sector will be the 2 to the power 21, to the power 21, right? Equal to numbers of recording surface into 128 into 5112. So numbers of recording surface will be, if we solve.
So how did you get 2 to the power 21?
See, if the minimum numbers of bit required to access a sector is 21, so it will be 2 to the power 21 total numbers of sector. See, if there are 8, if there is size of the sector is 8, the total numbers of bit required to access is 3, right?
Right.
If there are 16, then 4, right?
Right.
So 4 bits required. So if there are 21 bits required, then to the power 21 total numbers of sector. right? Hello.
Right.
You got it.
Got it.
So numbers of recording surface equal to. If you solve, you can get 32. Then numbers of platter records, right? So numbers of platter will be 32 by 2 equal to 16. Any doubt in this question?
Sir, what you have written in the first line is the generalized formula.
Yeah. See, total numbers of sector equal to numbers of recording surface, then 128 per track per surface, then 512 sector per track. That's why you have written.
Okay.
So write it and 2 raised to the power 21 parts.
Okay. If there's let's say one example, if there suppose the total numbers of sector is 16, how many bits we can identify? We can bits. Okay, if there is total numbers of sector is 2, you can identify 0 and the 1, right? Using 1 bit you can identify. If the total numbers of sector is 2, you can easily identify 1 bits 0 or 1. If the total numbers of sector is 4, you can easily identify using the 2 bits 0 0 0 1 1 0 1 1, right? If the total numbers of sector is 8, you can easily identify using the 3 bits 0 0 sorry. There is if there is 8, so you can easily identify using the 3 bits, like so if there is total numbers of sector is total numbers of sector is 8, you can easily identify using the 3 bits. So minimum bit is required is 21. So total numbers of sector will be 2 to the power 21, right? So you got it?
Yes.
Okay. Any doubt in this question?
So conversely, if you give us the sectors, and if you ask us to find the number of bits, it will be log that sector.
Yeah,
log
it will be log.
Okay.
It will be log. So yeah.
Hello, Subhendu. Yeah. Hello.
Yeah. Yes.
Hello. Yeah. Am I audible? Subhendu?
Yes, you are audible.
Yeah. So in this question, you can see that in the number of platter, it is not mentioned the how many surfaces used. One sided of the surface of the platter or both side of the surface is used or not for the storing information, right? It is not given in the question, you can see. So by default, you have to assume that the both side of the surface is of the platter is used for storing surface by default, if it is not given explicitly. So you need to mind it. Yeah.
And also in some places I've seen that the top disk and the bottom disk have only one surface. So we just don't worry about all that, right? We always assume that it's going to be two-sided.
Yeah, if it is not given.
Right.
If it is given, so the one sided of the platter is a store information. So then you have to consider only one surface. Otherwise, you have to consider always both sides by default. I'm talking.
Okay.
Yeah. Is it clear to everyone?
Yes, sir.
Okay, let's move to the second question, last question. So considering a string pending block references in the order given below 32413 24142, the system has a buffer with 3 slots. Assume that the buffer is empty. If LRU buffer replacement policy is used, what will be the numbers of misses and numbers of hits? We have to find the this is 2 into numbers of misses plus 3 into numbers of hits. So we have given 3 numbers of buffer slot, right? So let's given B1, B2, and B3. And the block reference is given 3, 2, 4, 1, 3, 2, 4, 1, 4, 2, right? So if LRU buffer replacement is used, so when you give 3, when you it's only request to 3, so 3, but none of the buffers present 3, so it will be a miss, right? It will be miss. Everyone got it?
Yes, sir. Yes, sir.
So while when request of two pages, so 3, then 2, it will be also miss. When you request to 4, so 3, 2, 4, it will also miss. When you request to 1, but you can see that the 3 buffer is already full. So which block references is not been used last long time, that will be removed, right? So you can see that 3 is not used last long, so 3 will be removed. So 1, 2, 4, and this will also miss. When you insert 3, so you can see that 2 will be. Hello, am I audible?
Yes, sir.
Yes, sir. Audible.
2 is
2 will be
recently used.
2 will be listed.
Okay.
LRU.
Oh yeah. Okay. So 1, 3, and 4. When we insert 2,
Miss.
then 4 will be removed.
This is also
Yeah,
a
this
miss.
also miss. And then 1, 3, 2, like so. When we insert 4, 1 will be removed, right? So 4, then 3, then 2. While we insert 1, 3 will be removed, right? So 4, 1, then 2. This also miss. This also miss. This also. When request to 4 blocks, so it will hit, right? So 4 is already available. So 4, 1, 2. This is hit. And on request to 2, this also hit. 2 is already available. 4, 1, 2. So you can see the numbers of misses 1, 2, 3, 4, 5, 6, 7, 8. The number of hit is 2, right? So 2 into 8 plus 3 into numbers of hit, 3 into 2. So 16 plus 6, right?
Correct.
So,
numerical answers I will add.
yeah. So yeah. So any doubt in week 8? So in week main thing is let me say. In week 8, main thing is tree. We have already discussed in week 8 activity session. You can go through it, and whatever we have questions we have solved in the PR deck session or in the numerical, those are the important numerical and BST and the magnetic disks. So you have to find so in magnetic disk we have one tutorial in 8.1. We can go through it. This will be very helpful. Any doubt in week 8?
Yeah, so any doubt in any of the week 5, 6, 7, 8? For week 1 to 4, you can just go to the summary slide that we have released last quiz. And yeah, this time also we have released. You can go through it. Like week 7 and 8 are mostly theoretical parts. So that's fine.
Sir, whatever you just did, or all the possible questions from week 8?
VCAT, like, yeah, it will be similar to practice and graded question.
Okay.
Yeah. So you can just go to the practice graded and mock question, activity question.
Okay, sir.
Yeah. Okay then. Thank you.
Sir, one question here.
Yes.
Big omega and big O. How this type of question is also there in the graded. How to decide on that? This has been not covered here.
Omega.
Big O.
Big O notation.
Notation. Algorithm asymptote.
Okay, so see.
Whether question will be there from that part or not?
No, that is in activity question, right? Those things.
That will not covered in this.
You can just go through the slide. Yeah, it will be directly from the slide also.
In graded also it was there, so I asked whether it will be covered in the question quiz 2 or not.
You can just go through the slide. That we cannot tell directly, right?
Yeah, I gave it. Okay.
Yeah.
Okay. Thank you.
Yeah. Okay. Thank you
so much.
everyone.
Thank you so much.
Yeah. Thank you, sir.
Thank you, everyone.
Thank you for watching 3-hour movie session, like technical movie.
It was interesting, nevertheless.
All the best. All the best.
Yeah, all the best, everyone. Yeah.
Thank you.
Thank you and all the best.
Thank you.
Thank you, sir.
Yes, sir.